is that D-instanton perturbation theory, okay, has some divergences. Then we identify the origin of those divergences, and then we also describe how to resolve them, okay, at least to the extent we could. Okay. But we found that the divergences are not fully resolved. Okay, that well, divergences are fully resolved, but we get the wrong answer. Okay, so there is something missing in that approach. Okay. So what we will try to understand today is what exactly is missing. Okay. And in this context, we need to understand open string field theory a little better than what we have done so far. Okay. So what I will do first is to say something about string field theory. Okay. I will be focusing on open string field theory because that is what is really needed for this, but the general formalism also applies to closed string field theory.
Sorry, quick question, Ashok. Could you, yesterday you explained that we didn't see the zero mode problem in the calculation that you
Yes.
you talked about, and could you say physically why that was so?
The zero mode problem?
Yeah.
Yeah, that's because that if you have 4 phi's, this is what the amplitude you are calculating, right? And the point is zero mode would have come if there is a phi propagating here. If there is a phi propagating here, that would have been a zero mode. You will see 1 over 0. See, the zero modes give problem only if there is an internal propagator which along with the zero mode propagates.
Okay. So, if because phi has something to do with the instanton. I was thinking that if an instanton here contributes, why doesn't an instanton there contribute to the same process? There's a whole manifold of instantons.
Yeah.
And but because phi itself has something to do with moving the instanton, I suppose.
Yes, exactly. Yeah. I mean, in hard point function, it will contribute, right?
Yeah.
I mean, if you are considering something like this, it's just that because of the symmetry, right? 3-point function of phi is 0, right? But 4-point function of phi, right, would contribute in general. Yeah, because we have x goes to minus x.
Function 0, that's physically a relevant answer because the phi's themselves have something to do with the instanton. Had you been looking at some insertions of something else, instantons everywhere would have contributed, like just in space, just in time.
Yeah.
And therefore the zero mode would have shown up because you would have had.
Yeah, meaning if you are trying to calculate like closed string 2-point function.
Right.
Right? Yeah. Suppose you have trying to calculate closed string 2-point function. Right. There the phi could have propagated in the intermediate channel.
Yeah. And that was physically clear because instantons everywhere in time would have contributed to the process.
Exactly, yeah. Okay. So what we need to do, so we need to understand open string field theory, okay. But before that, we will try to understand the open string Hilbert space. This is just a review of what is well known, but it will be useful for formulation of string field theory. Yes. Yes. Yes.
So that can be shown to be true using the wordsheet method that you described yesterday.
The
cubic and psi and so on.
Yes, that's right. So for that particular string field theory, right? If you use that, so that corresponds to a specific choice of f1, f2, f3, right? And if you choose those f1, f2, f3, you see that the S, T, and U channel diagram covers the whole moduli space. You don't need anything.
Oh, that's why cubic.
That's why you can only work with cubic. Right? What I describe is a more general formulation where you need all kinds of vortices. Yeah, so Witten's theory certainly is a special case of what we have discussed. Okay, so to build the open string Hilbert space, we want to do mode expansion on upper half plane. So we expand C as sum over n, Cn z to the minus n plus 1. Okay. I will explain this B as sum over n Bn z to the minus n minus 2, Similarly, del x as sum over n alpha n z to the minus n minus 1. C bar in fact is not, doesn't have any independent expansion. And so on. And then if there are other fields like Liouville field and all, you can try to do similar thing, but you don't really need to do that. Okay. So the idea is that these expansion, these numbers, okay, are fixed by the conformal weight of the field. Okay. So that this is typically the expansion is it's like z to the minus n minus h. Okay, and depending on what the conformal weight is, C has conformal at minus 1, that's why it's plus 1 over here.
So it's the same mode expansion except that C bar n is equal to Cn.
Exactly.
And B bar n is equal to
Yeah, and that's because of the fact that you put the boundary condition that C equal to C bar
Right.
for Z real. Right, and similarly.
Without the BC things, I understand that as you know, the T being equal to T bar.
Yes.
Across the thing, and with the C's, what gives these things? I mean.
This is basically C is associated with some diffeomorphism, right? And you allow diffeomorphism so you do not move the boundary.
Also, it's directly from the parameters of the different.
Exactly, yeah. So in terms of this, we define vacuum. This is the SL2R invariant vacuum, and this is defined such that C of 0 on vacuum, B of 0 on vacuum, del x of 0 on vacuum. These are all well defined. Okay, namely they don't diverge because vacuum means identity operator, right? So if you bring a C close to the identity operator, nothing should happen. So this implies certain conditions, namely Cn on vacuum should be 0 for n greater than or equal to minus 2, Bn on the vacuum should be 0 for n greater than or equal to, sorry, n greater than or equal to 2, this is minus 1, alpha n on the vacuum equal to 0 for n greater than or equal to 0 and so on. Okay, alpha 0 in fact doesn't exist. Alpha 0 is like a momentum, but as we discussed, open strings don't carry momentum, so alpha 0 is identically 0. Okay. And the state operator correspondence is basically state operator correspondence basically says that V of 0 on the vacuum, this if V is a vortex operator, then V of 0 on vacuum is the state, and this we denote by V. Okay. So for example, from this you can easily convince yourself that C of 0 on vacuum is just C1 on the vacuum. Okay. Just use that expansion, okay, and put Z equal to 0 and use these relations. Similarly, B of 0 on the vacuum is B minus 2 on the vacuum and so on. We also have the OPs, the singular part of the OP, B of plus non-singular, which I will not write down. Similarly, del x of z, del x of w is 1 over z minus w square. Okay, of course, all of these depends on the normalization, but I will not worry too much about the normalization. And from this, it follows that BMCN anti-commutator is delta m plus n0. alpha m alpha n commutator is m delta m plus n0 and so on.
So the relation between alpha bar m and alpha m, whether it is plus or minus, that depends on whether it is Dirichlet or not.
Exactly, yeah.
So that's being assumed.
Yeah, exactly. Right, so I'll work only the alpha m's, right? Alpha bar m's are dependent, so as long as you only use alpha m's, you don't have to worry too much. Yeah, worry about that. Okay, so from this we can build the states in the Hilbert space. So states in H, okay. They are basically built by these oscillators acting on the vacuum. Okay. So Bn, B minus n, C minus n, alpha minus n acting on vacuum. Okay. Of course, for non-zero n's, so let me write down the condition C minus n. So here n should be greater than or equal to minus 1 because C1 doesn't annihilate the vacuum, so even C1 is okay. Here n should be greater than or equal to 2. Here n should be greater than or equal to 1 and so on. Okay. And of course, you also have the V of 0, okay, right? That also can act on the vacuum because this is a vortex operator from C equal to 25 theory. Okay, again we will not really need too much about this. But the full Hilbert space is built by all of these. Yes.
So what is the vertex operator from C equals 25? Sorry.
Because I said that the full CFT, right, is a CFT of BC
Plus whatever
x
is needed to
plus whatever is needed to make the central charge 26. Right. So there is a C equal to 25 CFT, right? That's
could be Liouville itself.
yeah, could be Liouville itself. Right. So basically, you think of these. You don't worry about what these are. Right. So you, instead of the vacuum, you take V, the state V, right, which corresponds to some primary, some state of the Liouville theory. Right. Primary, secondary doesn't matter, and then we apply all these oscillators on that state. Right. That's the way you build the full open string Hilbert space.
C1 on this vacuum and B0 of C1 on this vacuum are the two lowest energy states.
Yes, C1 on the vacuum and C0 C1 on the vacuum. B0 annihilates it. See B0 B1 B1 B minus 1 annihilates it. B minus 2 onwards is what is non-zero. So C1 on the vacuum is a tachyon, the standard tachyon which has m square equal to negative m square.
And you say C0 on vacuum is also
Non-zero, yeah, because you see that we apply C minus n for n greater than or equal to minus 1. So C minus C1, C0, C minus 1, all of these can be applied on the vacuum.
C minus 1?
Well, vacuum, by vacuum we will always refer to the SL2R invariant vacuum, but that's not the lowest L0 state. Right? C1 on that is the lowest L0 state.
C1.
Yeah, and C0, C1 on that is also lowest L0 state because C0 doesn't change L0 value. Right? By definition, C minus n increases the L0 value by n. Right? So the lowest ones are C0 on the vacuum, sorry, C1 on the vacuum, and C0, C1 on the vacuum.
And the vacuum corresponds to the vertex operator C and C del C. Two lowest
Yeah, the two lowest energies, exactly.
C and C.
C and C del C, exactly.
so the thing that propagated in the middle yesterday when there was a phi and phi,
Hmm.
there was a del x, C del x and C del x. So the stuff that propagated in the middle was just a C.
Yes, exactly.
That was this thing.
That's right. Right, which gave the divergence, the quadratic divergence. We saw that alpha square coming in, right? The leading term was alpha square, which of course are cancelled at the end.
Right.
Okay? But that was just because of the tachyon, the C1 on the vacuum. Yes. Okay. So now we come to string field theory. Okay. So open string field which I will denote by psi is an arbitrary state in H. Now this may sound a little confusing, right? How can a field be a state? Okay. But the general philosophy is not very different from what to do in second quantization, right? Because in second quantization you take the wave function or the first quantized formulation, right, which represents a state, and make them into field operators. Right? So in that sense, wave functions becomes fields in the second quantized theory. Okay. But more specifically, let me say what one means by this. Okay. So let us suppose that we have a basis of H, phi r. Okay. Then any state psi can be expanded in this basis, sum over r chi r phi r. Okay. And when you say that the open string field is a state in H, what one means is that these are the dynamical variables. Dynamical variables of SFT.
Psi operator creates the state psi.
Yes, you can think of this. So the field, so the open string field here you said it's a state, but you can also think of open string field as a vertex operator in the CFT, right? Arbitrary vertex operator, because there is state operator correspondence, right? But if you want to see it as normal field theory, right? Field theory has some dynamical variables, right? Over which you do path integral. That's these ones, these coefficients.
And field operator roughly creates an electron at that position.
Yes. So we are not going to field operator it. We are not going to do canonical quantization. Right? We will do path integral quantization. Right? We will basically carry out path integral over these fields, but with some qualifications. We will describe later how to carry out the path integral properly. Right? But at this stage, just think of these as the field components. Right?
And normally they fields because the phi r has a p index, a momentum index.
Exactly.
But here, in this case, there's no p index.
That's right.
So it's just a bunch of.
So it's a zero-dimensional field.
Yeah.
Right? I mean, there is really no. So it's just ordinary integral. It's not a path integral.
Yeah.
When you try to do integration,
An integral with an infinite number of.
exactly, integral over infinite number of variables.
So this is like if it was in standard second quantized string theory.
Hmm.
Because the vertex operator.
This is like psi x and x get and sum over all x's.
Yes.
That I'm giving it notation calling psi get.
Yes.
We're not doing much.
And if there were discrete variables, then I would do the same thing.
Yeah.
Psi
The
x.
point once you say it's a state, right? You can expand in any basis.
Yeah.
You can either expand in the x basis or the p basis, right? Those will give the origin, the field or the Fourier transform of the field.
Invariance, that's the invariance.
Exactly. Yeah. Is this clear?
So the coefficient of vertex operator e to the ipx would be the phi p.
Yes. If there was, yeah. So this if it was not D-instanton but some other theory, then the sum over R will also include integration over some momentum, right? Because the states will be leveled by momentum, and these will have to be then interpreted as the Fourier transforms of the appropriate fields. The field in the but written in the momentum space. Okay, but here it's
Now
just
this is discrete because of
because this has no momentum, right? It is just a discrete set of variables. Exactly.
I can I understand the map, but just in terms of what we would do normally in field theory would expand in terms of some basis of creation and annihilation operator.
Oh, that's when you do second quantization, right? I'm just trying to rewrite the field theory because you will do path integral, not second quantization.
So, okay, so you're thinking of the analog of a
Classical actions, a first classical field, yeah, exactly. So when you construct a field theory, right? You first construct a classical field theory, and the condition you impose is that the classical field equation should be like the Schrodinger equation of the first quantized theory. Right? That's what we mean by Schrodinger field theory, for example. Right? You impose that the Schrodinger field, the classical equations that the Schrodinger field should satisfy is the Schrodinger equation. Then you quantize it. Right? That's the second quantization. Right now we are into the analog of the classical field variables.
I see. So this is the analog of classical field variable, but you have written it somehow in terms of state. So let me just understand that. So if I normally had a field variable, I would have to write the dynamical variables by expanding in some basis.
Yes.
And then wouldn't I have to specify both the value of the field and its momentum or something to understand the full dynamical content?
No, in path integral you don't, right?
Path integral, then
yeah.
you just specify the value of the
Yeah.
field.
Here they are just saying what are the dynamical variables over which you integrate, right?
This is off shell.
Hmm.
You're doing it over all
Yeah.
space and time.
Exactly.
So,
So this is just some basis in which you expand.
Exactly.
Got it.
Right? You have not even imposed an equation of motion. Okay, the equation of motion will be the analog of the Schrodinger equation, and then you have to quantize it. Okay. But this I should warn that is not totally correct, because what we are writing here, right, is in the BV formalism, but we will discuss that later. Okay, but let's not worry about that right now. Let's think of this as if it's a classical field theory.
and at the moment you're putting no host number constraint.
No, nothing.
All
Yeah.
host numbers.
Exactly. From the worldsheet perspective, this phi r can be any state in H.
Yeah.
Okay.
And it's not annihilated by B0, for instance.
Nothing. Yeah.
Just nothing.
We don't put any condition.
I mean, if you ask me nothing, since I know nothing about string field theory, I would have said, oh, here the field is a functional of, x of sigma and then
Except that x is like r. This r you can think of as the x's, but there's a continuous x here, right? So field is field is a function of x, right? So r is like the x index. Okay. If there are some actual physical directions, right, along which the field lives, then that will be included in the sum over r, right? It will be more like an integral, except that here you work in the p basis, not in the x basis.
If you think from space-time, it's clear. Because each state here is a particle in space-time. And
the
for
second quantized. I mean, I'm just trying to say, why is the
First quantized particle,
Yeah, what is first quantized?
e to the I p dot x.
Okay, that's a mode of the field, right?
No, but for the first quantized viewpoint, right,
Yeah.
e to the I p dot x is a wave function, right?
see, what you're trying to create a field theory of all the particles of string.
Yeah.
Yeah.
That's what you're doing.
Can I ask one question?
Yes.
Suppose you write down a field theory involving chi-r.
Hmm.
The classical equation of motion for the field theory will be the one cell condition for the state psi.
Exactly.
Okay.
Exactly. That's what we have to demand.
Okay. And then you quantize that.
Exactly.
Okay.
Okay. In fact, the linearized classical equation, because like in Schrodinger field theory, for example, right, the linearized equations are the Schrodinger equation, but then when you include the nonlinear terms, interactions, right, they describe particle interaction, right?
Yes.
Two particle going to two particle and so on. That's not contained in the single particle Schrodinger equation.
Yes.
From the point of view of space-time, what's odd is that you've got so many fields that don't correspond to anything physical.
Yes. True.
That's some huge redundancy.
Yeah. Because you are including all host numbers.
Yeah, right.
Those
But-
will be the on-cell conditions.
Yeah, on-cell conditions should eventually remove all those.
Getting rid of it.
Yeah.
Yeah, but you've done it by putting a huge number of auxiliary
Hmm.
fields.
Yeah.
Infinitely more auxiliary fields.
The DV formalism would be useful after we go on shell, right? In the sense that
No, it's hidden already. BV formalism is there.
I see.
Okay, but we will see why. Right now, just let's think of this as a field theory, right? And then we will see how exactly to quantize this, right? We are not talking about quantizing yet.
So far we have not. I mean, just to be clear, there's been no manifestation of any specifics of the algebra, whether it's open
No,
or
nothing.
closed.
Yeah, yeah, exactly.
I see. So it's the analog of, as you all are saying, that you take the particles and then, in a sense, the wave functions would have depended on target space coordinates, and you take all the particles and you make them into just some field.
Exactly. Yeah. So you think of say e to the I p dot x, right? That's a possible wave function.
Correct.
Okay. The on-shell condition is p square plus m square equal to 0. right? The Klein-Gordon equation will give p square plus m square equal to 0. So, that should come out as an equation of motion, but when you construct the field, right, you take psi of p, or the Fourier transform as an arbitrary function of p, right. Then you impose p square plus m square psi equal to 0.
Yeah. For every particle in string theory, we have a Klein-Gordon-like field. The only thing that's funny is that we have Klein-Gordon-like fields for many things that are not particles.
Exactly, yeah.
Right.
Well, I mean, even in field theory, you have A0, which is not a particle.
I know, but this is a huge
Yeah.
redundancy.
Yeah, I agree. The A0, there is a particle for A0, right? But you include that as part of the fields.
The only thing, sorry, but you must go on, of course, but the only thing is that this is more a first quantized going to, you're not yet at at the fields corresponding each of the particles which has been made up into a string field. You're taking a Schrodinger, you're taking the first quantized particles and just putting them together.
That already has the fields. I have introduced the Klein-Gordon field, right? Suppose you are a relativistic Klein-Gordon particle.
Yes.
What this has introduced is a Klein-Gordon field.
Is that right? I see.
Yeah, because any, I mean,
So the Klein-Gordon field would have had the creation and annihilation.
no, classical Klein-Gordon field.
So that would have had
A of p and A dagger of p. Exactly. And these are the Fourier modes.
R is like space.
Yeah. Sorry, you had a.
One I think of this is like taking the quantum Klein-Gordon operator and acting it on the vacuum. And then it would be like a sum over one particle states, right?
Yes, that is true. That's the way you go back to the first quantized. You make the corresponding with the first quantized description, right? But we are not trying to do that yet, right? We are simply saying that given the first quantized formulation, right? I want to write down first the classical field theory, right? Then we will of course quantize it, right? And then when you quantize it, it should give us back at least, and the field limit it should give us back the usual particles. That's okay. Okay, so now I have to say what the Grassmannality of this chi-R's. Okay, so chi-R, this again is a surprising thing. Chi-R is Grassmann even or odd if phi r has Gauss number odd or even. So, Gauss number, let me remind you. Yeah, C has Gauss number 1, B has Gauss number -1.
An identity operator is Gauss number.
Yeah. So, Gauss number C has 1, C and C bar. B and B bar have -1. The vacuum has 0 and all matter fields have 0.
So this would give the tachyon Gauss number, make it tachyon and even.
Yeah, tachyon is an even field. Okay.
So all the usual fixed vertex operators of string theory
Exactly.
would be
Exactly.
even. So that's
So that's why we said that fixed vertex operators are more natural, right? So this one, right? If you take T times C1 on the vacuum, suppose you are expanding. Suppose you are expanding psi in a series, right? So this one is Gauss number, is Grassmann even, because this has Gauss number 1, right? So odd Gauss number means Grassmann even coefficient, right? T is a tachyon field, right? Then there will be phi C1 alpha -1 on the vacuum. Okay. This, the corresponding vertex operator here is C del x, right? That you see is a 0 mode field. Okay. This again has Gauss number 1, so this will have this will be Grassmann even, okay, and so on. Okay. But if you have, for example, C0 C1 on the vacuum, right? Call this coefficient what? Xi. This has Gauss now. This is Grassmann odd because this is Gauss number 2. Okay, or the vacuum, just the vacuum itself, right? eta times vacuum. This is also Grassmann order because vacuum has those numbers.
Psi is also tachyon, right? The zeta or
It's the same.
This is yes. This is also tachyonic, meaning it has L0 minus 1. Yes.
But we normally
M
throw
square.
it away in world sheet string theory, right? We impose the condition B0.
If, okay, we may or may not want to do it. We'll see.
Okay.
Yeah.
We may not want
Yeah.
to do it here.
So we'll discuss. Yeah, we'll discuss that gauge fixing or whatever later.
Right now, you have not imposed any conditions from the Cohen BRST Cohen.
No, no, because BRS that will be part of the equations of motion, right? So you are not imposing that yet. Now, what may surprise you is that how come you have Grassmann odd fields, right? Because you are doing bosonic string theory, right? In bosonic string theory, there are no fermions, okay? And the reason, as we will again see later, is because this formalism, okay, is in the BV formalism, where all possible ghosts that you will ever get while gauge fixing are already there. Okay, we don't see any gauge fixing here, right?
So we have not fixed any gauge.
We have not fixed any gauge.
Done anything.
Exactly.
Everything.
But BV formalism starts by not doing anything, but including all the fields that could possibly arise in your theory. Okay, so that's the way BV formalism works, and it is hidden. It just happens that this formalism is naturally formulated in the BV formalism. Okay, which I am yet to describe. Okay, what this is.
does this also happen for the quantization of a point particle rather than a string?
I think for point particle you can do BV formalism, but you have to put those things by hand. It's not that, yeah.
This doubling is not automatic.
Yeah, I don't think it happens automatically for the point particle, as far as I know, but I am not completely sure. For membrane, I think nobody knows even how to quantize properly, right? So, yeah. Okay, now the subtle point. Okay. So, when I said that this is a field, okay, naively one would think that then you only need the action and then you start doing path integral. Okay. And while doing path integral, if I encounter some gauge invariance, then you fix gauge and so on. Okay. But again, that is not the way this formalism works. Okay. You are never instructed to start with a path integral, that is for all the chi-Rs. Okay. And we will see what the actual prescription is. Okay. In the BB formalism, the actual prescription is something else. You never have any anywhere a starting formalism where you integrate over all these. Okay. But again, this is just to keep in mind. We will see later exactly what the procedure is, what the prescription is. Okay. So, given the field configuration, okay, what we need next is the action, right? Because action should be a number. Given the chi-Rs, action should be a number that is generated, that is a function of the chi-Rs. Okay. So, the action has a simple form. Well, the kinetic term has a simple form plus interaction terms, okay, which are cubic and higher order in psi.
This is BRST.
This is BRST. QB is the BRST charge. So, let me write down.
By construction, it will give me the equation. BRST invariance is automatic. At least in this order, first order.
Yeah, in this order, the BRST invariance is automatic. So, QB is the BRST charge.
You said you are not going to allow me to integrate over all the
No.
variables. So
No.
it's not clear now.
Yeah, it's not clear now. We will see. It's more or less okay, but we have to see what we should integrate over. So, QB, let me write the expression formally, is integral over around 0 okay, roughly it's like this, but you can write in terms of mode expansion. Tm is the matter stress tensor, which involves the x field as well as the c equal to 25, whatever you have there. Okay. And the important point is that QB square is 0. Okay. So, roughly you can see from here that the linearized equations is QB psi equal to 0. Right? That is the condition for BRST invariance. Right? The state is physical if QB on the state is 0. Right? And again roughly there is a gauge invariance when you change shift psi by QB lambda, right? The action does not change, right? So, you mod out by that gauge invariance. So, the equations of motion tells us the QB on psi should be 0, that is the condition for physical state in the first quantized formulation, that is the analog of p squared plus m square equal to 0 for Klein Gordon. Okay. But in this case there is also this gauge invariance where you can shift psi by QB lambda, and that does not generate a new configuration. Okay.
So
but again
interaction preserves that property as well.
interaction preserves that property. We have to just modify that by nonlinear terms in psi. Okay. So, psi it is not just psi goes to psi plus QB lambda, there will be terms of order psi square, psi cube and so on in the transformation law, and then the interaction also preserves
I
that.
have a basic question.
Yes.
If I expand psi in the most general basis,
Yes.
and I just evaluate this first part,
Yes.
is it that all possible combinations will appear or some of them will be missing in the first, before I use equations of motion at the level of action?
No, not all possible combinations will appear because some of them are just QB on something.
Right. So,
Right.
so they will not appear. Therefore, I don't have to. If I really want to get the equations of motion, only those things that appear, I roughly have to vary their counterparts.
Yes. The other ones are arbitrary. Those are the gauge transformations.
Huh.
Those are gauge symmetries, right?
Those are case symmetries.
So, those are not fixed by the equations of motion.
Yes.
Yes. So, when you expand it out, right, the ones which appear, right, they are more or less set to 0 by equation of motion, that is the quadratic level.
Right.
The ones which do not appear are the solutions, are the non-trivial solutions, because they can be arbitrary, right?
It can be arbitrary, yes.
Okay. But some of them are just QB on something else.
That we have to throw out.
Exactly.
Yes.
Yeah.
And if we just take this BRST cohomology, we normally get twice the physical spectrum.
Yes.
And we have to put the B0 on states as that.
Yeah.
Will come somehow.
That will come. So, the point is this is only very at a sketchy level, right, because as I said, because it is BV, it is not like a classical action that you have written down whose equation of motion you have written and the gauge invariance you have written. Things are more subtle, okay. But at a rough qualitative level you can see the equation of motion coming out and the gauge invariance coming out. Yes.
Also, there are these two choices. One of them was nice, one of them was bad. That should also naturally come out. That
Okay, we will see what is nice, what is bad. Yeah.
one of them gives delta functions in its matrix.
Delta function.
Even B0 equals 0 or C0 equals 0. Which of the two vac you have to choose?
Okay. Yes.
So the interaction terms will change the equation of motion?
Yes, it will.
So should I think of that as changing the BRST operator? Or
No, I think the interaction terms are like, yeah, you can think of that for any given any solution to equations of motion, you can so that you can always define a operator, linear operator, which squares to 0. So, that is the modified BRST operator. Okay. But these are again at the classical level, in quantum level things get a little more complicated, right. But roughly there exists a BRST operator for any classical solution of the equations of motion. Okay. So, this you should take with a grain of salt because this is not going to be strictly true.
But just to ask, sorry, I didn't quite follow, but how much freedom do we have in the interactions?
Well, in interactions we saw that we have this choice of f's. The 3-point function, for example, includes this f1, f2, f3, right, which are arbitrary. So, you have a lot of freedom in the interaction, but again the point is that what one can show is that all of these are related by field definition, because you really do not have any freedom in that sense.
And is it true that for say superstrings the interactions go on to arbitrary orders?
Yes.
3.4?
Yeah, even for bosonic string, right, if you put arbitrary, if you put a generic choice of the FIs, it will go on forever.
And yet despite that, up to field redefinitions it's a unique.
Exactly, that is right.
This mirrors the fact that on string well sheet theory, if you've given the rules for propagation, you've also given the rules for interactions.
Yes, exactly.
So there's no freedom.
Yeah, meaning this reproduces the string world sheet results, right. But okay, maybe it's not completely independent, but somewhat independently, right? If you just demand that this is fully consistent, namely it satisfies the BB master equation,
It will also come.
then yeah, it will also completely specify, right?
It's incredible, right? I mean, so far, Einstein, diffeomorphisms don't completely specify anything.
Yeah. Yeah,
So high amount of
Much more powerful
It's
than
incredible.
yeah,
any field
It's
theory.
amazing. We get used to it. It's incredible.
yeah. It's just
Is there a choice of F's in the closed strings which lets this action truncate?
no,
Only in the ones.
only no. At least nothing is known. What I know for sure is that it is not possible to do it with a cubic vortex. Okay, that has been proven. Okay, but it has not been proven that it's not possible to find any vortex for which it truncates.
So, sorry, I know nothing about this. Please explain. But Witten's original formulation had only a cubic. Right?
Yes.
So
So
it's
that
not
that is an open string field theory. That's a special choice of F1, F2, F3 that I described yesterday. Okay. So that for that particular choice of F1, F2, F3, you get the Witten's vortex. And then what happens is that now if you calculate again the ST and U channel diagrams, they fill up the whole moduli space. Right? So you don't need to add the 4-point vortex. See, yesterday the way we did it, right? We saw that only a very small region near the boundaries are covered by the ST and U channel diagrams. Everything else has to be covered by the contact interaction, right? And the point is this is useful when you are trying to do perturbation theory because you have more control. Okay? But if you want, I mean, for a different kind of analysis, right? Certainly having a cubic theory is more useful. Okay, it's just so the point is because everything is related by field definition, right? You can use different versions of string field theory for different purposes, right? Because something may be useful for one purpose and some other thing may be useful for another purpose.
So Ashok, in Witten's theory, if you take the zero modes, is there a way of just getting a cubic quantum field theory?
If you take just the zero modes, no. Once you integrate out the rest, then it becomes non-cubic.
It hides the fact that there
Not
is
integrate out, but just low energy approximation. So just a deep, like n equals 4.
Yeah, but see the point is if you take the zero modes at the external state, right? In the internal state, everything propagates, right? So you have to sum over those to get an effective field theory of the zero modes, right? So what one can say, if you do that, right, you still have a solution to BV master equation with only the external zero mode states, but now it's no longer cubic because like in the S channel diagram when the heavy states propagate.
But those are very suppressed, right, in effective field theory. Those terms are going to be very suppressed. So let's say I'm not interested in those corrections. I'm just interested in very low energy fields.
Well then, yeah, you will get just zero. Nothing will depend on the zero modes, right? Because
I mean, the way I get n equals 4 super n.
okay, if you want to get n equal to 4 super Young mills, say not on D0 brand, not on D-instanton, but on a D3 brand, say, right? I think the 4-point interaction is not suppressed. Otherwise, you will not get a quadratic coupling.
But should this not be suppressed by the mass scale?
No, I think, yeah, so dimensionally, I mean, it's not really suppressed, right? Because quadratic interactions really come from there.
And the things you're integrating on include these zillions of auxiliary fields, right?
Yes, exactly.
So you do Hubbard-Stratanovich, you can make something look cubic, but actually it's quadratic.
Yeah,
A lot of that will be happening.
yeah.
Open topological string theory, that is,
Yeah, I think for open topological field theory, you can integrate, I mean, most of them are gone, yes. Exactly, yeah. Yeah. No, I mean, I don't know, nobody has really done, I mean, formulated this in the Hamiltonian sense. Right?
Is there a symplectic structure, for example?
The Hamiltonian structure, no, nothing is known because the point is if you really think of this as a field theory, it's highly non-local interaction, right? Even in time. So it's not completely clear how to go to the Hamiltonian formulation if you use this.
Actually, I wanted to ask something else, which is, does it have a good initial value formulation?
No, it's not clear. Yeah, it's not clear if it has a good initial value formulation. But you can do S matrix calculation with it, right? I mean, that is one thing you can do.
But as you emphasized in your public talk, the S matrix asks a different question from the initial value formulation, where you specify the initial state to be and then say.
But I think the point in principle S matrix has that information. How to extract it is complicated,
Yeah.
right?
So So it should probably have it.
Yeah, I mean once it has a procedure for S matrix, right, you should be able to extract.
Yeah, it's a different question as you
Yeah.
say. So, okay, but it seems very well worth proving, trying to prove.
Yeah,
right?
yeah. I mean that, I think you don't need, you can try to prove it in general. That if somebody has given you the S matrix, can you use it to solve the initial value problem? Exactly.
Isn't this sort of like going from time ordered correlators to retarded correlators?
Sort of like that, yes.
Because one answers the question about given an initial condition, what's the final state?
Hmm.
The other one answers the question of what is the S matrix.
Yeah,
And we know that the analytic continuations do that.
yeah.
But what I mean is, how much initial data do you need to specify? Because
Hmm.
this has got very high derivatives
Yeah.
and so on, right? To determine the future protein.
Yeah,
We expect it to be the usual thing.
yeah. We expect it to be the usual thing in the sense that you have to specify the initial data for all the physical fields, right?
Including
Metric
the
as well as all the heavy string states, the physical heavy
the
string
first
states.
time derivatives.
Yes, exactly,
We expect it to be what you get in free string theory.
exactly. Yeah. For free string theory, there is a confusion, right? Because that's this one.
But I mean, okay, but with the interactions, you need to show that.
Exactly. Yeah.
And, okay, I don't, yeah, but okay, how one gets it from the S matrix
Yeah.
is,
Yeah.
right, something.
Yeah. So I think that one can try to solve this problem in general without referring to string field theory, and then see if there are some additional subtleties when you try to do that in string field theory.
Can you say it again? What was the statement about? Is I don't want to integrate out any field. Keep all the fields. Then
Yes.
is it the statement that there is a way of writing down the full theory by writing only up to cubic interaction?
No, no. There is, for particular case of open string field theory, it is possible. Okay, that corresponds to using some special f1, f2, f3 that I introduced yesterday. Those three functions, right? That's a particular cubic vertex. With that, you can get the open string field theory completely. Okay. But putting the closed strings in that picture, in that formulation, is a little tricky.
And then you need to add all.
Yeah.
So again,
I was just going to say, in this case, of course, you just get some function of t, phi, psi, eta. I mean, they're not dependent on anything. In your case of the zero.
Yeah, D-instanton, exactly.
case,
Yeah, exactly.
There's just some function.
Yeah, here there is no initial value problem.
Right.
It's not a function of any coordinate.
And so you just have this
Yeah.
function, and now you have to.
Exactly.
thank you. Again, can you check question? Is there a limit in which one can get something that looks like oscillator theory?
Looks like Vasiliev theory. Yeah, I don't know. I mean, it has a lot of higher spin fields, but I don't know whether one can actually get Vasiliev theory from here.
With some star product or in Witten's language,
Hmm.
but not in general, right?
Yeah.
The special thing about Vasiliev theory is that it's got only one rotation.
Yeah,
Looks like much more.
yeah,
So you take a limit somehow.
yeah.
So you mentioned that in the BP formalism, the whole thing is very highly non-local. Does it have to do with the fact that in all the auxiliary fields now, there's a derivative acting on them? I mean, they're
No, no,
not
non-locality is
algebraic.
much severe because the interaction terms have exponentials in momentum. If you
I see, okay.
if you actually do it for extended branes,
I see.
it has exponentials in momentum. I mean, that's what is responsible for ultraviolet finiteness, because those exponentials in momentum, right, makes the loop integrals finite in this language. But the price you pay is that you don't have a good initial value problem, at least in this formulation.
And also the auxiliary fields are not purely algebraic. When we
They also, yeah, they also have exponentials in momentum kind of coupling. Yes.
So in the formalism, so you said extra fields are only represented as, do you mean the anti-fields or?
No, no, we don't introduce any extra fields. It's already there, right?
Are these odd ones the anti-fields or?
We'll describe soon. We'll describe how BB formalism fits in this.
So it fits exactly this.
Exactly. You don't need anything else. Yeah. So normally you want to do BB formalism for a gauge theory. You start with the gauge theory and then you add all these fields, right? Here everything is already included, right? I have to just say how they are included.
Is there a reason for why?
Why? It's not clear. It's not completely clear why it's included, but it so happens that BB formalism seems to be exactly suitable for accommodating this.
Sorry,
Yes.
Just one last, since this is such a great intro for me for string field theory.
Like yesterday I gave F1, F2, F3,
That
right?
was very explicit.
So everything is known explicitly in that sense.
When you go to higher and higher orders.
Yeah, so it's known, I mean, okay, I mean, there are procedures for describing the interaction, some particular choices of Fs, right? That people have done. Recently, for example, this Zoibach and Costello wrote the string vertices based on hyperbolic geometry. Okay? So that gives a specific choice ways to construct these Fis. Okay? Now, if you want to construct them, write down those Fi functions, it's probably you have to do work, right? It's not that somebody has already given the functions automatically, but that gives an algorithm.
These were the three functions.
Three functions F, right? And the similar things will appear in all higher orders, right?
More and more functions appear.
Yes, exactly. Because for 4-point function, you have to introduce 4 local coordinates, right?
So then you have to find a way to construct them in any
Exactly.
field, a choice of field variable.
Exactly.
But all of them are basically equivalent up to field definition.
Exactly.
So
That's right.
basically there is only one interaction. That, I mean, the interaction is basically unique.
Yes. Interaction is basically unique. Yeah. Up to field definition, it is unique, right? Either the given formulation of string field theory uses those Fis when you do the
For instance,
calculation.
in open string field theory, all open string field theory, whatever you could write down, they are all equivalent to, for example,
Witten's theory. Exactly.
Theory up to field definition.
Exactly.
Because all of them are equivalent to the same string version.
Yeah.
So it's like the same Polyakov thing describes the cylinder as well as the Pants diagram.
Yeah. Exactly. Yeah. Okay. So now we have to say in what sense this is, I mean, it's already in the BV formalism, right? Now, in what sense you are not supposed to integrate over all these chi-Rs that I introduced. Okay. So let me now introduce some more notation. So what we will do now is we will choose a final basis. Which I will call phi r and phi r. Okay. So this has ghost number less than or equal to 1 and this has ghost number greater than or equal to 2.
Ashok, sorry
Yeah.
to disturb, but if you have the energy with a break, we can go until 1 o'clock.
Yeah, that's fine. Yeah.
Only we want a
Okay, yeah, no problem. Yeah. Yeah, okay. Okay, so we break up this into two sets of basis states, okay, and we impose the condition that this is the orthonormal basis. Okay. Now this is possible because we have this condition. This is the way we normalize the vacuum, okay, because we said yesterday that we need 3 C's in a correlation function to get a non-zero answer, right? And we also wrote down the 3-point function of the 3 C's that translates to a normalization of this form. Okay. So you need a total host number 3, right? So since this has host number less than or equal to 1, this has host number larger than or equal to 2, it's possible to pair them so the inner products are 1. Okay. The one state from here, one state from there, but it also follows from this that this is 0 and phi is equal to 0. Okay,
Yes.
because that's ghost number,
Yes,
conservation,
ghost
right?
number.
Because this has ghost number less than or equal to 1, this has a less than or equal to 1. So this can add up at most to 2, okay, whereas this has always at least 4.
And many of these guys will have no pair. Guys
No,
will have-
everything will have a pair.
What if it has very high ghost number?
It has a smaller
Oh,
ghost
it's,
number, yeah,
absolutely low as well.
exactly. Yeah, so both sides, so everything is paired. That's why we can choose this.
Just something built with a lot of B oscillators.
Exactly.
That's the-
Yeah. Right now they are just there. Yeah, nice. Yeah, because they are paired.
And the normal physical states of string theory have host number 1.
Yes, exactly. Normal physical states have host number 1. So they are in this. Okay. So now I am going to write psi in a slightly finer way. Okay. Sum over R, psi R phi R plus psi R phi R.
So this psi upper R and psi lower R, are they in some sense canonically conjugated?
Yes, we will see what they are. Right now this is just a decomposition. Okay. And so now the point is we will declare, okay, this I should say, okay, I have ignored some up to R dependent signs. Okay, we will not really need to know those, but just if you want to do calculations, we should fix the signs properly. Okay, but right now,
Sorry, this maybe you probably said that.
Yes.
Is that a definition of the, this defines the pairing between sets?
yes, exactly, exactly. So this defines the pairing. So the upper R and lower S, right, are paired this way.
So you define something, if you know what you mean by lower S, you define what you mean by
Upper
upper
R,
S by
yeah,
the
exactly. That's right.
You can choose a basis upstairs and downstairs and use the usual dot products, usual inner products to check if they satisfy this condition or not.
Yeah, and it is always possible to find a basis which does this, right? Because everything has a pair.
Up to R dependent overall sign or relative sign?
Well, R dependent, yeah, relative sign. Now, this may have a R dependent sign, this may have a different R dependent sign, but that's the thing that I have not written down explicitly. Yeah, but it's just to caution you, there's no really tricky point there. It's all known what the R dependent sign is. Okay, because the various formulas that I'm going to write down will depend on that sign. So now, we declare that psi r are the fields and psi r are antifields.
Is this familiar from quantum field theory?
No, this is BV.
BV.
In,
and
yeah,
BV
if you do BV formalism of quantum field theory, then you introduce the antifields explicitly, separately.
There would also be brackets and anti.
Yes, we will describe it. Yeah, we will describe the bracket. So this is field and antifield. Okay, and now let me just give the procedure for path integral, even though that's not what we are going to use eventually. Okay, so the path integral is done over the fields after setting the antifields to 0. Okay, then imagine that you are trying to do some path integral, right? I said that you are not supposed to integrate over everything, right? So you are supposed to integrate only or part of it, and this is a prescription that you do path integral over the fields and set the antifields to 0.
In the action.
In the action everywhere, even if you have some operators whose correlation function you are trying to calculate, some physical operator, gauge invariant objects, there also you set this to 0.
So this is some sort of partial gauge fixing in the.
Yeah, see, it's not really gauge fixing. Okay, as we will discuss, this is gauge unfixing.
I see.
Okay, so what this describes in physical terms, I am going to discuss soon.
Sorry, Ashok, does this give a well-defined path integral? That is because you have so much redundancy and so on.
We'll describe. Okay, the point is if you are doing lattice gauge theory, it will give a well-defined path integral. If you are doing perturbation theory, it will not. Okay, it's like gauge unfixed version of the path integral.
I see.
Okay, as we'll see soon.
But all the gauge unfixed paths are compact.
If it's compact, yes, exactly. Okay, that's what will happen in lattice gauge theory. Yeah, yeah.
Suppose you want to do it in some gauge theory, gauge quantum field theory.
Yes.
Until this inner product was very special to 0 modes.
No, not to 0 modes. This is for everything.
No, the fact that 3
Yes.
That was related to zero modes.
Well, zero modes for the, yeah, the oval fit zero modes. Yes.
Yes, was in
That's
that
right, yes.
language. I have
Conformal killing
that
vectors. Yes. Yes.
So that was very special to this particular kind of gauge theory, and if you want to use gauge. But in more general, less general quantum field theories, if you want to do this formalism, then is there a natural pairing?
No, because generally quantum field theories, right, don't come with antifields.
Right,
This is very special to string field theory. That has already come to with antifields, right?
Right.
In quantum field theory, if you want to do BV formalism, you have to introduce the antifields by hand,
Okay.
right? So that notion of antifields is not even there in standard gauge theory.
And that is special because of this zero.
Yes. Okay. Now, what happens if you do this is the following. Pardon?
So,
Yes.
extra fields that you have in double field theory, for example, those are also not there.
The extra fields that you have in double field theory. Okay, I mean, what some of them come from string field theory, those are there. Otherwise, no.
So that doubling is again artificial.
Yes, that's right.
Where we include both.
Yeah, yeah, exactly. Yeah, yeah.
But there you also.
Because there you introduce this even in a non-compact case, right? So here in the non-compact case, you will not introduce any winding like degrees of freedom. In double field theory, I mean, you double fields, so whether those are, yeah. I think it's just a way of rewriting supergravity, right? It's useful for some things, but it's not a new different field theory.
I was just trying to look for places where there's some doubling required to describe objects in a more unified way. Just trying to see if
Yeah, no, I think this is BV. I mean, it's not really double field theory because that's not a, there is no anti-field there, right? What to do there? Okay.
BV comes in field theory also if you have non-linear gauge transformation stuff.
Yeah, I think if the gauge algebra closes only on shell, then BV is a useful formalism.
Because I remember in Weinberg there is a
Yeah.
little section of
Hmm.
BV which I think involved some kind of a non-linear gauge transformation or not. Maybe I'm
See, nonlinear, of course, even Young Mills you can say is nonlinear, right? Because it's not.
I think it's just with open algebra.
I think it's for open algebra is when you need BV. That when.
no, even to first order. I mean, it's like L mu omega plus omega commutator A.
Yeah.
So, and then there is an A square. No, maybe I'm remembering it.
See.
There's something, some non-linearity involved in.
I see. Okay, I don't remember.
So, suppose you have some theory and you have some symmetries, you want to put certain boundary conditions.
Yes.
These boundary conditions may or may not resolve those symmetries. So, at this stage, it is not clear that this boundary condition will not break the gauge matrix.
No, you are not putting it on any boundary. This is just a,
boundary
yeah.
condition.
See, this is just, I mean, if you do D-instantons, right? There's a boundary. It's just point.
I agree. So,
Yeah.
I was thinking R as space coordinate, and then you are setting some field. So, you have two kinds of fields, psi upstairs and psi downstairs. And one kind of field is zero. This is some sort of a boundary condition for the path integral, and that might not go well with your.
Well, this is BV tells you to do that, right? So what I'm saying is that now let's see why this is not always useful. Okay. So what happens here, okay, is the following. That okay, I have to say something more. That what one can show is that the action, the terms in the action, the endpoint coupling. Okay, if you take a endpoint coupling, in the action is non-zero if and only if the total Gauss number adds up to n. Okay. That all the fields, suppose you have a there is in the interaction term, right? You have a generic interaction term. The total Gauss number has to add up to n. Okay. Now, by setting psi r to 0, right, we have ensured that psi is sum over r psi r phi r, okay, and this has Gauss number less than or equal to 1. Right? So this basically means that only the Gauss number 1 field enters, right? Only Gauss number 1 field enters the action.
QB has Gauss number 1.
Well, that's the kinetic term, but it's true also for all the interaction terms.
For the kinetic term, you said it has to now. So I have two sides,
Yes.
which gives me, let's say, I take Gauss number C and C. So 2C plus QB has, let's
One,
say,
exactly.
Gauss number 1. So
That's
2C plus 1 is going to be
Yes,
3.
that's right. So for kinetic term, you can just explicitly examine it and see this, right? The total Gauss number has to add up to 2
Right.
because QB supplies 1.
Yes.
But I am saying this is also true for all the interaction terms.
Which you didn't even write.
I didn't even write those, right? But it is true, right? 3-point interaction that I wrote down, right? That you can see. F1 dot V1, F2 dot V2, F3 dot V3, right? They are the V1, V2 and V3 Gauss numbers have to add up to 3, right? Otherwise the 3-point function will vanish.
Yes. So they was C times del x kind of.
So this is true for everything, right? All interaction terms, I have not written them down, but all interaction terms have this property. Okay.
So the quartic guy will be roughly a 4-point term with its explicit insertion of some
B.
Gauss number -1.
Exactly, that's right.
In the kinetic term, when you take the inner product,
Yes.
both sides have RL downstairs, right?
Yes, so in this case what will happen is that the both sides have to be downstairs because the only term that survives, okay, is a Gauss number 1 terms, right? Because anything that has Gauss number less than 1, right, because all the antifields have been set to 0, right, they cannot be compensated, right. So S depends only on psi of Gauss number equal to 1. Okay. So here you can give a nice interpretation of this path integral.
Sorry, I should just.
Yes.
Sorry, I'm
Yes.
trying to do that. So, given that phi r only has Gauss number less than equal to 1,
Yes.
and given that all the Gauss number 2 and above fields are set equal to 0, then you are saying only Gauss number 1 can enter. Huh?
Exactly.
If less than 1 is entering, then you are in trouble. Just repeat once
Because if less than, because you cannot compensate
you cannot compensate.
by a Gauss number larger than 1,
And total Gauss number must add up to
n. If you have n external states, it has to add up to n, right? So each has less than 1, right? Less than or equal to 1. So unless each of them have 1, you got.
So what is this vector space operation that you want to do to write a higher order interaction term?
Okay, basically you have the 4 insertions like f1 dot v1, f2 dot v2, f3 dot v3 and f4 dot v4, right? But then there is also a b insertion. That's the way you build a 4-point interaction vortex, right? Because every time there is a modular integral, right? This 4-point contact term should have a y integral, right? Each y integral of that kind will be accompanied by a b. Otherwise, you don't get an invariant measure, right? This is Beltrami differential. So that's why the total Gauss number always adds up to 1.
Right. No, I had a simpler question. So how do you write down, let's say, a cubic vortex using the states? Because you are now working in the Hilbert space.
Yes. So I said f1 dot v1. Let's say q1. Yeah. f1 dot v1 0, f2 dot v2 0, f3 dot v3 0. Right. So the way so this will be given. Let's use the chi-r notation. Chi-r, chi-s, chi-t, f1 dot phi r 0, f2 dot phi s 0, f3 dot phi 3 0, sorry, phi t 0. Okay, there may be some signs because I have taken the chi's through the phi's, right? So some graspability is there. So this is just a number, right? So you will get some cubic function of the chi's.
And the quartic guy will involve one vertex operator integrated?
Yes, exactly. One vertex operator integrated, or it may not be just one vertex operator. It's some integral, right? Which may move two vertex operators simultaneously, but there is one integral that will be
As many integrals as D-insertions.
exactly. That's right.
So if one wants to write this as some kind of inner product between two states, as a three-point function, then can you think of it as fusing two of those?
Yes, you can. There is something called the square bracket product, right? You can think of this as fusing.
That was what I was
I see. Okay. Okay. So then what? In this case, the integral that you have is in fact quite simple. So you have integral d psi ghost number 1 of e to the s. This depends only on psi of ghost number 1 times a completely decoupled integral d psi of ghost number less than 1. Okay, there is no s dependence on this. So this just factorizes. Okay. In fact, it has a nice interpretation. It basically says that this is like dividing by the volume of the gauge group. When you do a gauge theory, right, you have the integral over the gauge fields, and this is like dividing by the volume of the gauge group. Okay. Because what this effectively what this does is it makes the gauge transform. The ghosts that enter here, that the Grassmann odd objects, are like in one-to-one corresponding to gauge transformation parameters. Right. So when we integrate over those, it's like bringing something in the denominator. Right. So this is like volume, defining the volume of the gauge group. But in any case, this just completely factorizes of the integral, right? So you can just forget about this. Okay. And this integral is what you can perform.
So if I take as ghost number 1 psi and I make a gauge transformation, it will go to always less than 1.
No, it will remain 1. Gauge transformation parameters are typically okay. The physical gauge transformation parameters have ghost number 0, so the psi remains ghost number 1.
Yes, so
But
they are in the same.
exactly. But right now we are not talking about gauge invariance, right? See, this is we use BV. See, that formalism I have never said. Okay, I said gauge invariance, but that was only to motivate you, right? I wrote down an action, okay, and then I said that this is the way you quantize. You set the psi r to 0, psi lower r to 0, right? Anti-fields to 0.
Yes,
Okay. What you get is this integral
yes.
by doing that.
This is clear.
This is clear?
But then you had a motivation from Walsh perspective. You had a motivation that these are the legal primary operators roughly.
No. Here, these all ghost number 1 fields are being integrated over,
All of them are there. So
but they are not primary necessarily.
In particular, the one that are right there also there.
Exactly.
But then you had some motivation for these less than ones are not just gauge orbits.
No. Yeah. So okay, the point is that ghost number, the leading. Suppose you take the physical fields which have ghost number 1, right?
Yes.
The transformation law is delta psi equal to QB lambda, right? So that lambda has ghost number 0. Okay, so those corresponding fields are here. Okay, so it's like as if the gauge transformation parameters have become integration variables, and you are integrating over those. Okay, and so it's like by dividing by the volume of the gauge group.
But that all automatically happens without any Faddeev-Popov.
No, yeah, exactly. Oh, no, but the point we will see. I mean, this is formal, right? But there will be a problem with this. Okay, the problem will be not that this is wrong. Okay, is that you cannot do perturbation theory with this. Okay, and we will see why. Okay. So this is clear, right? So this you can just factorize and forget about it, right? Because nothing depends on this. Okay. Now the question is, can we do this path integral? Okay, or can we do this perturbatively? Okay. This you can do provided the kinetic term is invertible, right? Okay. But in this case, what happens is the kinetic term is not invertible because kinetic term operator is QB, right? Okay. And any state of the form QBS is annihilated, is 0. So the kinetic operator has lots of 0 eigenvalues. Okay. So it's not that this is wrong, okay, but with this you cannot really do perturbation theory, right? You cannot invert the kinetic operator and write down Feynman diagrams. Okay. If you could do something like lattice gauge theory, you could possibly evaluate this. Is that clear?
On a computer, that's fine, right?
On a computer, yeah, okay. If you could do string field theory on a computer, maybe it will be.
But many of these gauge variances will be non-compact, right?
Could be non-compact,
So I
yes.
don't think even on computer.
Yeah, the point, okay. It's not that it will be, we don't really know if it's compact or non-compact, but I mean, on a D-instanton, for example,
Okay.
I mean,
Say,
yeah. whether the gauge invariances are compact or non-compact.
Yeah, yeah.
Right.
You were saying we don't know, no? It could
Yeah,
be
meaning, yeah, I don't know, yeah.
We only know them infinitesimally.
Yes, you're saying we don't know the measure of the space of the parameters. It looks
Yeah.
like parameter goes to infinity.
Yeah, not the measure, yeah, whether there is a compactness.
Whether you have to
If you do U1, right, it's like, I mean, whether there is a compact direction, yeah, exactly, whether it's circular real line.
That should be built into your formalism. I mean,
That's, okay, at least the way it is formulated, it's not built in, right? You can declare them to be compact. Once you have written it in this way, right, you can somehow declare them to be compact, but it's not, as I said, I don't know how to do this in practice, okay? So what I'm saying, this is formally correct, but it will be hard to implement this, right? This is just this is what you start with in any quantum field theory, right? Gauge invariant path integral, right? You start with this and then you, yeah, then you get stuck, right? You have to do Fourier-Popov, okay? But here you are not going to do any Fourier-Popov, okay? Because everything is already there, okay? So we'll see what we need to do.
Sorry, so I thought this factor, sorry, go ahead. I thought this factor thing is the redundancy.
Is
The factor integrals are the redundancy in this.
exactly, yeah.
But then
No,
in
no.
addition to that,
No, this is, yeah, the factored things are like dividing by the volume of the gauge group, right? But this integral has redundancy, right? So it's basically dividing by,
redundancies are
roughly here,
large as that.
exactly, roughly cancelled by this, right? Because the Grassmann, opposite Grassmann parity, right? Those redundancies are cancelled by this.
I mean, but the surprising thing is that the volume of the gauge group
Hmm.
has come out isolated
Automatically.
without me doing any Fourier-Popov already. I mean, gauge fixing.
No, but this is fully gauge invariant path integral. You have not factored it out.
That's fully gauge. I see. Fully gauge invariant thing. Wait,
Divided by the volume of the gauge group,
So
right?
you mean if I could do this in terms of gauge invariant variables,
Yes,
then it would be all okay.
exactly. That's right.
I see.
Right? See, in lattice gauge theory, people just evaluate this, right? You don't.
even when we discuss Fourier-Popov, we start by saying the integral measure is dA divided by integral.
Exactly. That's right.
So this is really the starting
Yeah.
point.
Yeah, this is the starting point of the gauge theories, right?
Yes, yes.
Integral over the fields.
I don't see it coming out separately.
No, by divide. When you write the gauge theory path integral, right? You write something in the numerator
Yes.
and something in the denominator before you do Fourier-Popov or anything, right?
So you're saying that this, the Gauss number, the first factor
Is what is in the numerator.
original path integral divided by stuff.
No, this is the original path integral.
Yeah.
This is what is dividing it by the volume of the gauge group. See, in the normal path integral, right, you write integral dA
Coming down, okay, I didn't understand.
e to the s.
I'm
And
sorry, sir. It's something coming down. It's a.
this is effectively something coming down because it's Grassmann, opposite Grassmann parity, right? Yeah.
Oh, it's 1 over the.
It's not 1 over. It's written as product. But because it has opposite Grassmann parity,
The effect is that it's inserting 1 over.
yeah, exactly.
I see that.
Yeah.
That was my.
Yeah. Okay. So now we have to develop some more formalism to see what one does here. Okay. So we have the notion of anti-bracket. Okay. So anti-bracket. Okay. Now we are again going back to the full formalism. Okay. No psi r setting equal to 0. Okay. So given two functions of the size, this is like a Poisson bracket. Okay. This is defined as okay. So you see, this is like Poisson bracket, as if this is coordinate, this is momentum, right? Except that these are not really usual coordinate and momentum because the Grassmann parities are opposite, right? You can show that the psi upper R and psi lower R always have opposite Grassmann parities. Yeah.
What is del RF?
Okay, these are right derivative and left derivative because these are Grassmann, can be Grassmann odd, right? So right and left derivatives are different, okay? Just differ by signs.
Given one f, I can associate with one state. Or one
No, f is in general can be a nonlinear function of the size. F and G are any arbitrary functions of the size.
Any arbitrary function of the size. Okay, I really want to understand. Can you say what this bracket is in?
This is the definition of the bracket.
Right,
This is like the Poisson bracket. This is like the Poisson bracket, right? With these regarded as coordinates and these regarded as momentum, right?
And F's are functions of psi upstairs and psi downstairs.
Yes, that's right. F and G are functions of both. It's like when you calculate Poisson bracket, you have functions of Q and P both, right? So F's are functions of both.
And this subscript, capital R and capital L.
Oh, these are right derivative and left derivative. Because these are Grassmann, can be Grassmann odd, right? So you have to say whether the derivative is taken from the right or left. Is it okay? No, there is no intuition. It's just saying that it's as if the division that we have done, psi upper R and psi lower R, are like canonically conjugate pairs, right? But that's about it. It's just an analogy, right? It's not really true because they have opposite Grassmann parities. Okay? But just like in if had they been canonically conjugate pairs, right? Then in the path integral we will not integrate both of our coordinates and momentum,
Right.
right?
It is some polarization.
Yes, so you have to do a Lagrangian submanifold, right? And the particular example that I described, okay, is one such example.
One such.
We have kept the psi lower R's to 0, right? That's like setting all the momenta to 0.
Right.
Okay, but this analogy will be useful because like in normal classical mechanics, you can first make a canonical transformation, define new coordinate and momentum,
Right.
and then set the new momentum to 0, right?
You can choose different polarizations.
Exactly. So we will do the same thing here.
It feels okay. Actually, the same thing. Let's.
Yeah, I mean this is part of BV, okay? But let me just say something else, okay? That the action satisfies a good identity. That's crucial.
All this is consistent because we have in standard pictures. All this is consistent because we have a very nice non-degenerate closed form.
Yeah, here also, right? Here also there is a non-degenerate closed form because for every upper side there is a lower side.
Which is the one that takes you up from down, because you have given me commutation relations, Poisson brackets, which
Yes.
means that you have given me those matrix elements.
Yes.
He's giving you the canonical
Yeah.
basis. Basically.
Yeah, I have given the canonical basis, right?
Right.
Sorry. Yeah. So this is what is called the BV master equation. No, quantum BV master equation. Okay. So classical is just this part. Okay, this is the Poisson bracket of S with S, right? There are two terms here, but if F and G are the same and they are Grassmann even, then you can show that these two terms are equal and up to a sign, and you get this. Okay, this is half of the Poisson bracket of S with S. This part is what is called the quantum part. Okay. This one corrects for the possibility that the measure may not be gauge invariant. This you can prove that the action that you write down in string field theory, that nonlinear action, right, satisfies this equation. Okay, this you prove by using various identities in the worldsheet theory.
So this is it's not a consequence of the Poisson bracket.
No, no, it's something that you can verify independently given the action that I wrote down. Right, I have only given the first term in the action, right, but the whole series, right, including all the corrections, okay, that whole series satisfies an equation like this.
Now in standard phase-space formulation, if you give me action, I can get what is my symplectic form. From there, I can get what are my.
No, here it's not like that. Here it's not like that. Here this is the what I have given, right, is like P q dot minus S,
P q dot minus S.
right, like the Hamiltonian, because I have given it as a function of both Q and P.
That is fine.
Okay, and I have separately defined what is Q and what is P,
Yes.
psi upper R and psi lower R, right. So the symplectic form is already has been specified separately.
Oh, okay. Wait.
See, because we specified this condition, right, phi R phi S equal to delta R S.
So you have given me the symplectic
Yes.
Now, in standard classical mechanics, I given an action, I should be able to derive my symplectic.
But I have not given you the action, that's what I am saying. I have given you the PQ dot minus H, which is not, see, action normally is given as a function of the coordinates only, right?
Right, and S is the analog of Hamiltonian.
It's the Hamilton analog of PQ dot minus H, you can say.
It's function of both positions and moment.
Just one. This S is the action you wrote earlier.
Yes.
And I should think about this equation as PQ dot. So S is supposed to be understood as the Hamiltonian in classical phase space.
No, I mean, I think that analogy doesn't go that far, right? It's not really Hamiltonian in classical phase space, right? I'm just saying that if, so, but let me finish what is the useful. This is an identity that S satisfies, right?
S satisfies this identity because of equations of function?
No, because you can explicitly check. You take the S that I have, right? The kinetic term plus all the interaction terms in string field theory. Not every S will satisfy this. The S that you get in string field theory.
So this is specific to string field theory. This
No, anything that has BB formalism, right?
Will
S is constructed to satisfy this, right? But in string field theory, the S that you get automatically satisfies this.
okay.
Okay, but so far this is just off cell S, so you didn't use equations of one.
No.
It's a some identity.
Yes,
It is something like
Exactly.
independence. So let's go.
some identity.
Okay.
Okay. Now let me, yes.
So if you had the A's written somewhere here, the first kinetic term and interactions, so this equation will be satisfied term by term, or the whole thing will be satisfied?
Well, this equation will give various parts of psi.
Okay.
So every part of psi will be 0, right? The coefficient of every part of psi will be 0. So it's in that sense yet it's term by term, but it's not that every term satisfies this separately.
It's clearly non-linear.
Yeah.
Yes, right, yes. So,
Yeah.
okay.
Also not homogeneous.
You have to
Yeah.
get the full,
2S and
full
1S.
infinitely many terms in that.
No, you can check up to given order in psi,
Yeah.
right? Expansion in psi. So S is given as an expansion in parts of psi, right? Up to any given part, you can verify this.
It's just last time I asked.
Yes.
How should I think about this? You have given me position, momentum. you
No,
have
this
given
is
symplectic
not
structure.
position momentum. This is like position momentum, right?
Right.
Because for position momentum, the coordinate and momentum are both same Grassmann parity.
I know.
Yes.
But in analogy, you have given me those things and given me symplectic structure. How should I think about this?
How?
Is there any analogies that I should keep thinking?
Well, the closest analogy is, I said, coordinates and momenta, but not everything works here as in coordinates and momenta.
Because if it was coordinate momentum, then you could have set up a phase space path.
Exactly.
And
That's right.
certainly you would not have put P equal to 0.
Exactly.
That's,
Yeah.
I mean, you would
Yeah.
integrate out over here.
Exactly.
And you would get the right
Yeah.
thing. But here the description is different.
Exactly.
You're
Yeah.
saying put all the P's equal to 0.
Exactly.
Yeah.
Yes.
The BB formalism, should I think of this identity as telling me that if the action satisfies this identity, then the path undergo gives is a path undergo so a consistent quantum theory?
Yeah, then the path integral satisfies certain properties, right, which is that under a canonical transformation, the physical amplitudes remain the same. Okay, so that statement I have not made yet, but I will just describe it now, right. So the point is that suppose S satisfies this, okay, then
So if you kept track of H bar,
yes,
then the second term would have a.
yeah, second term has an H bar, yeah, exactly.
In fact, this equation can be written as just that second operator.
That's true, yeah, yeah, you can also write it that way, right, that the full thing applied on e to the IS over H bar equal to 0. Okay, so now the point is that suppose we make variable transformation
So now we are accounting for the ambiguities inserted by choice of F.
choice of
F, the functions F. I mean, if you, because.
no, so for a given choice of functions f, those fi's, it satisfies this, any choice, right, as long as those f's are internally consistent, right, it will satisfy this equation.
Those are field redefinitions. That's a
Yeah,
separate issue.
so that we have not even discussed yet, right, what happens when you change the f's. Okay. So the point is, if we make variable transformation, right, from this pair to say psi tilde r, okay, such that
You want to preserve the bottom line.
exactly Fg is equal to del rs del psi tilde r, sorry, del r f this has to be for every g, f and g, for all f g. Okay, that means the Poisson brackets written in terms of psi tilde are the same as the Poisson brackets written in terms of psi. Right? This is again the analog of canonical transformation, but here of course there are extra signs, right? So it's not really canonical transformation; it's like a symplectic transformation. Then, if this is true, okay, and given that S satisfies this, okay, then we can do the path integral by setting psi tilde r equal to 0. Okay, instead of psi r equal to 0, I could just set psi tilde r equal to 0.
But what happens to this equation in terms of variables? This is the Euler equation.
No, this equation remains the same.
This equation remains the
That's
same.
right, yeah.
So this is a nice
How
equation.
Yeah.
does that follows?
That follows, yeah, with various properties. Okay.
And then, sorry, you are saying if you could have set psi r equal to 0, now you can set psi r tilde equal to
Exactly.
get the same
That's right.
value.
If the original prescription I gave was that you set psi r equal to 0 and do the path integral. Right. Now we are saying that you can take psi tilde r equal to 0 and do the path integral, right, and you will get the same result for all the physical amplitudes. Yeah, so measure you take as d psi r, d psi tilde r. Okay. In fact, the non-invariance of the measure, okay, is somehow compensated by this. Yeah, okay, this Bataran and Vilkovitsky has a long discussion on that. It's not intuitive to see. Yeah, you have to do some work to check that that's what happens.
Because this involves only terms in the action, in the e to the exponential of action.
Exactly. See, the point is normally what happens is if this canonical bracket is preserved, right, then the measure is also automatically preserved. dq h dp remains dq tilde h dp tilde, right? Here, because of this Grassmann nature, a generic symplectic transformation will not preserve the measure, but of course it will change in a specific way. Okay, and what happens is that once you take that into account, okay, you find that once S satisfies this, okay, it automatically
Things will not
exactly. That's right. Okay, but in fact we will do a much simpler thing. We will not change the. We will make a linear change in variable, right? So that you don't have to really worry about the measure. Yes.
Can you write this equation in terms of this Poisson matrix? This equation, this Euler equation.
Yes. So in terms of new one, or in terms of Poisson bracket, not only in terms of Poisson bracket. No,
What are the things that goes in?
it goes this structure, right?
This is a new structure.
Yeah, it's a new structure. This is basically there because the quantum measure is not invariant. It's precisely to compensate for the quantum measure not being invariant that you need this.
Is that called the Laplacian?
Pardon?
That operator.
Yes.
It's the BV Laplacian.
Yeah, it's like a BV Laplacian. Yeah, yeah.
Just the IH bar, I mean,
It's accompanied by H bar. Yes.
I
I mean, I have not written the H bars, but this is I mean, because it's accompanied by H bar, right? You clearly see that this is coming at quantum order, right? The non-invariance of the measure is being compensated.
It's actually the Laplacian acting on
E to the IS by H bar.
over H bar.
Exactly.
So then it's just the Laplacian equals.
That's right. Exactly. Okay, but again, let me say that for what we are going to do, we don't have to worry about the measure because the change of variable will be linear. Okay, so I'll now give an example of such canonical transformation, okay, which we are going to use.
So you are going to say there are good choices agree with
because the original choice psi tilde are equal to 0, right? Even though it was correct, it had this problem that it had that gauge invariance, right? You cannot do perturbation theory with it.
Oh, so you are isolating. I see.
Yeah, you cannot do perturbation theory, right? Because the QB had a lot of zeros,
Yes.
right? So now we are going to see how to repair that.
If you take a particular psi and make psi going to QB of chi,
Yes.
transformation, and if you try to calculate the current associated with it,
Current. No, see, if you set psi, if you take QB psi, QB chi, right?
that does
Uh,
not enter at all.
No, that QB acting on QB chi is 0. So QB has zeros, right? That's why you cannot invert the kinetic term.
Yes, that was the point why you have 0 modes.
Exactly.
Suppose you have a gauge theory, suppose you have a classical gauge theory. And
Yes.
Then you have your symplectic structures.
But that symplectic structure has nothing to do with this one. In classical gauge theory, you don't have the antifields, right? This is a completely new structure from the classical gauge theory viewpoint.
On the phase space you have also attacks.
But that has nothing to do with this one. That's the point, right? This is not
Gauge, okay, let's.
the psi tilde, the psi upper R, right, is a completely different kind of fields, the whole new set of fields, right? This is not the cause of the canonically conjugate momenta to the classical gauge fields.
The term which is proportional to h bar in the Bezier equation,
Is the
the term
that's the quantum correction to the BB master
yeah,
equation.
Can I think it's like the one loop exact quantum correction?
Yeah, in a sense it's one loop exact, right? But to solve this, you may need to add to S terms of arbitrary or higher power in h bar.
And that can be also be computed from starting from the string field theory action and performing one loop computation.
Yeah, so string field theory action, there's an independent way to construct string field theory action,
Yeah.
right, to all orders, right? That's by demanding that you get the correct covering of the moduli space, right? That is also can be regarded as a solution to the BB master equation. That is, if you didn't worry about the covering the moduli space, right, but just say you start with the 3 string vertex and then you want to keep adding terms so that you satisfy BB master equation, right, you will arrive at string field.
Is it a well-defined equation that you
Up to ambiguities, at every order you will have ambiguities. Yes, exactly. Because you miss, say, some terms, right, say some psi to the 4 terms, you have to add that to compensate, right. Then you miss some psi to the 5 terms, you have to add that to compensate and so on.
So in a sense, it gives a correct covering of all of moduli.
Exactly. So if you start from a 3 string vertex and try to build the whole BB solution to BB master equation, you will automatically have to add all the higher order terms in the action.
Perturbatively one can construct that just from one loop computation of the
Exactly. Perturbative, that's the you do.
Yes. I was wondering for the path integral for doing perturbation theory, I mean, at least in principle, can one do perturbation theory by just confining the attention to the BRST cohomology and where the
Yeah, you can do that except when you have divergences, right?
Okay.
That is the problem. That's what you are trying to deal with, right?
I see.
So there you have to use some string field theory like
So
formulas.
the string field theory automatically cures such
Exactly.
divergence.
Right? We saw that it cures, but we also saw that it gave the wrong answer. So we are now trying to figure out what was wrong, right? Okay. So now let's introduce new basis. New basis, which I will call phi tilde r and phi tilde r. Okay. This time we are not going to use ghost number to label them, but we will just say that B0 acting on phi tilde r is 0 and C0 acting on phi tilde r is 0. Okay.
You had phi and you had phi variables in which you had some conditions.
Which variables?
Before you make the canonical transformation.
Yes, we had the capital, we had the phi r and phi, yeah, these ones. There it was ghost number, right? We say that these are ghost number less than or equal to 1, these are ghost number greater than or equal to 2.
So now make canonical transformation. And
No, we have not said it's canonical transformation, we are just introducing new basis. We are giving an example of a canonical transformation, but you have not constructed the canonical transformation yet, right? We are just giving a new basis of these, right? Now, new basis satisfies this, and we will demand that they are orthonormal. Okay. And you can also verify that this is 0. Okay. Earlier these were 0 because of the host number conservation, right? Now the way to see that this is 0 is that you can just insert identity, which is B0 C0 plus C0 B0. Okay, this is the B0 C0 anti-commutator, which is 1. Right? If you insert this, right, you see phi tilde r. This is annihilated by C0, right? Okay. So on this side, this will kill this, and this will kill this. Right? So that's why this is 0. Similarly here, this will be killed by B0, this will be killed by B0, the two terms. Right? So that's why this is 0. Okay? So we can choose a new basis like this. And now we can expand psi as sum over r psi tilde r phi tilde r plus psi tilde r phi tilde r. Okay. And it's an exercise, you can easy exercise to check that this is canonical transformation, this is symplectic transformation. So exercise is that this pair psi r to psi tilde r is symplectic.
This curly bracket means set, not also bracket.
Yes, yes, set.
What do you mean symplectic? That means
That Poisson brackets are
is
preserved.
preserved.
Yes, exactly. Okay, that Fg when you calculate with psi tilde is the same as Fg that you calculate with psi tilde psi. Okay, so let me write this again. So del F del, this is the right derivative, psi r and this is the same as del r f del psi tilde r del L G Okay. So which means that psi tilde r's are also good variables in which you can carry out path integral, okay, by setting the psi tilde lower r to 0. Okay. So define path integral by setting psi tilde r equal to 0. Is that clear?
So, the way you presented with the without tildes before, because that had a manifest pairing, that's why you chose that.
No, that I chose that because that was the original gauge invariant definition, right? I wanted to show how to use get the usual gauge invariant path integral, right? Because in that form, if you choose the psi lower r to 0, right, you get an integral, right, where you only have the classical fields that you integrate over, right, and divided by the volume of the gauge group. That was the correct expression, except that it was not very useful for perturbation theory. Right? This is going to be useful for perturbation theory.
Ashok, how does it follow that you get this correct answer by setting psi tilde r equal to 0?
Yeah, because it preserves Poisson bracket, right? And then BV formalism says that as long as the S satisfies the master equation, right, under a change of variable which preserves a Poisson bracket, you get the same answer.
the same answer, but that would mean if you go to the tilde variables, you'll get the same answer.
If you go to the,
If you go to the psi tilde variables from the psi variables,
yes,
you'll get the same answer.
exactly.
But then how does it follow that you can set this to 0 and get the correct answer?
Because prescription is always the psi tilde lower have to be 0, right?
So when you
Because you never do a path integral with everything, right? That when you say you get the same answer, it's with this, right? That half of the variables have to be set to 0. Yes.
So these tilde antifields
Yes.
from the original fields and antifields.
Yes. So basically the point it's I mean it's actually simple canonical transformation. It just declares some part of the fields as antifields and vice versa. It is some exchange, right?
From here we can actually see that because we insist B0 and something is 0,
Hmm.
we have to include something from the other equals.
Exactly, certainly. So the point is fields and antifields get mixed.
So that's why the two sets mix.
Exactly, that's right. So the point is the original set, what you are doing path integral, which was only host number less than or equal to 1 set, right? That is not the same as this set that will be doing path integral over, right? Otherwise you will get the same problem,
Right.
right?
So if these are linearly related, the
Hmm.
old basis and the new basis, then some linear combination of the psi tildes will be 0 modes of QB, no?
We'll see. We'll come to that.
Now the both
With-
numbers of the interacting vertices are not n, right?
Are not?
N, because if the n is the
No.
endpoint now
No,
because
the interact, that is still true. The total host number has to add up to n, right?
but the individual ones are not a plus one.
Exactly. The individual ones are, so now everything participates in the interaction, right? Because now there is a constant on the host number of the state, right? So let's see what constant to put on the state, right? So the state on which you are integrating over is sum over r, psi tilde r, phi r, right? Phi tilde r. Okay. So this satisfies B0 psi equal to 0. From this. You have defined the state phi tilde r as B0 phi tilde r equal to 0. So this is what is called the Siegel gauge. Even though in the BV formalism, you didn't see any gauge fixing anywhere, right? You just chose a different slicing, right? Different polarization. Okay. But you will see that now there will be no problem with the path integral. Well, almost no problem with the path integral.
But how does it happen? I mean, in the sense that the number of psi r's and the number of psi tilde r's are the same, no?
Yes.
So then, if there were 0 modes of QB in the psi r thing, then where did they go?
Because these are linear combinations of those, no?
These are linear combinations. That's
Exactly.
precisely the point. So
But these are not linear combinations of the variables which are remained.
Right, exactly, because you said.
Some variables you threw away, some variables you kept, right?
Exactly.
Here that set has gotten
I
altered.
see. Okay, so I see.
The fact that you're setting the tildes lower.
Exactly.
than 0, that's-
Yeah.
This B0 killing that is a definition of tilde.
Yes.
And then why is this a gauge choice?
No, it's not. That's the point. It's called Siegel gauge, but in the BV, right?
It's not to be thought of as a gauge.
It's not to be thought of as a gauge choice, right? It's just to be thought of as a different choice of polarization.
Still you haven't said anything about how kinetic term behaves in this new code.
We are going to do
You
it.
can have 0 modes.
We are going to say, yeah. So let me write the kinetic term.
So just to draw an analogy with the simplest things, we just try to give you formulation of say Youngmans.
Yes,
Then the place where the gauge fixing function enters is in this electric transformation.
that's right. Exactly.
So
That's
the
it.
tilde will be basically another antifield times the gauge fixing function in terms of original fields.
Yes, that's right. But here the way we set it up, right? You don't call it gauge fixing, right? Because the BV, the whole BV, the whole action is already there in string field theory.
Does this pairing differ only in the C0, B0 sector from the previous one, or it's more?
Yeah, in this case, yeah, it's like that. Earlier certain host number states you had set declared as antifields, some as fields, right? Now some of those antifields have now become fields,
Right,
and the corresponding conjugate have become antifields.
right, right. But suppose I take a particular state
Yes,
and I want to pair it.
yes.
In the old definition, you had given me a way of pairing.
Hmm.
The new definition, I also have a way of pairing.
Yes.
Do these two states differ differ only in the B0, C0 sector, or more seriously?
Yeah, in a sense they differ only in the B0, C0 sector, right? Because the inner product has to be non-zero, right? So it's just a question of what we are declaring as fields and anti-fields, right?
Right.
I mean, if you, yeah.
Right. So it's almost the same pairing except it's one two-state system.
Yeah, well, but the half the things have been differently paired.
I understand.
Yeah.
I understand.
So yeah, so it almost in that sense it's simple, but
Yes.
not that we have only changed a few.
Yeah,
Right?
It's a radical change, even
Yeah.
though it's just this.
Exactly. Okay, so now the point is that if you calculate half psi QB psi, okay, with psi satisfying the signal this condition, okay, then the only part of QB that can possibly contribute is C0 L0, because you need a C0 to get a non-zero inner product, right? If this is annotated by B0, this is annotated by B0, right? Then you can insert a B0 C0 plus C0 B0 and make it 0 unless somebody inserts a C0. Okay, so you have to insert this C0. So the kinetic term becomes half psi C0 L0 psi. Okay. And now this is invertible as long as L0 is non-zero. Right. So on most sectors it becomes invertible. Okay. So this tells us the propagator is B0 by L0. Okay, of course it has problem at L0 in the L0 equal to 0 sector, that's the 0 modes, right, which you will have to deal with. And this you can write, if you want to make connection with the world sheet theory, you write it as integral 0 to 1 dq q to the L0 minus 1. Okay. And this gives us the particular prescription that we used last time, right, that this q to the L0, okay, basically scales the coordinate, right, and then the fact that you are taking the inner product, right, means one of them have to be transformed by minus z goes to minus 1 over z, right. So that's why w prime, right, became minus 1 over w by q. Okay, this is the w prime w equal to minus q identification that we used. Yeah, that yesterday I used this, right. I am just trying to explain how that came, right. That you start with a coordinate system, right, associated with this. That's on one part of the, a propagator connects two parts of the diagrams, right. On one part you have some local coordinate, right. This q to the L0 basically scales it, right. Then you invert it because you have to, this inner product, right, you have to take a VPZ conjugate, right, that's z goes to minus 1 over z, and then you identify with the coordinate of the next, of the other side. Right. So this algorithm that I used yesterday, right, basically comes from this.
How do you see from here that W prime has to be related to W in this fashion from this?
Because it's like, if you think of, you are inserting a complete set of states, right?
So it's a 0 and infinity of the
Exactly, that's right. It is, on this side it is 0, on this side it is infinity, right?
But I would have used 1 instead of q.
No, the q is like the scaling, because first you are doing the scaling with q to the L0 minus 1, right?
Okay, I see.
So that's why if you get w by q, and then you get minus 1 over w.
And so you are supposed to do this and then do the Q integral.
Yes, exactly. So this is the gluing, right? You glue the two things, you get a new surface, right? And after that you are supposed to do the q integral, right? Whatever integral you get. That's what we did yesterday, right? The y integral you convert into q integral and did the q integral. Okay. So here, let's look at the problematic cases. Yes. Yes, yes. So I will just, maybe I should have said that. So this L0 that appears here is matter plus host. Okay. So that C del CB, right, that part gives a ghost L0. Right? This you can check that the C0 coefficient is just sum of the matter stress tensor plus gauge stress tensor. Okay. So, the problematic cases are the tachyon. So, now you have to only worry about the Siegel gauge states, right, because those are the only ones which are appearing, right. So, the states which are added by B0. Okay. So, tachyon state is C1 on vacuum, right. These are the L0 minus 1. Okay. But this of course you know how to deal with, right, because this basically says that you replace 0 to 1 dq q to the minus 2 by minus 1. Okay. The tachyonic divergences are dealt with just by using the fact that the right hand side is well defined, right, for L0 equal to minus 1, this is divergent. Okay. So, it is not real, tachyonic divergences are fake. Then you have the 0 modes. These are the L0 equal to 0 states. L0 equal to 0, thank you. Okay. So, one class we have already dealt with, right. So, this is C del x on 0 acting on the vacuum. Okay. So, this we have already seen how to deal with, right. So, to deal with this we basically, whenever you encounter integrals, so these contribute like this, right, because for L0 equal to 0 this integral will be like integral dq inverse. We have said that these integrals will remove, we will just set it equal to 0, right, because you do not want these states to propagate in the intermediate channel, right. We remove them and at the end we have to integrate over the corrective coordinates. Yes.
Can you not make a symplectic transformation so that the modes for which this is bad, L0 equal to 0, in the new coordinates that part is nice, that part is
You can do that, we will see, we will do something like that, but we cannot remove all the 0 modes that way.
So for others you have this this prescription, this gauge.
Yes.
But for the L0 equal to 0 sector,
Yeah.
you go to the other symplectic.
So, the point is even the other ones will have L0 equal to 0, right. So, we will see exactly what the problem is, right. See here there is no problem, right. I mean here you know physically that you cannot really integrate over the collective modes, right. So, you cannot get rid of this by any symplectic transformation.
But at the end you need to take the measure and do the integration.
So, no, measure is in BV tells you what the measure is.
Yes.
It is just integral over the fields,
Yes.
no measure, right. Everything is in the action, e to the s.
Yes.
Okay. So, BV measure is quite clean, right. So, there is no confusion about what the measure is
Yes. In this formula, yes.
in the BV formalism, right.
These are not gauge 0 modes, they are physical 0.
These are physical 0 modes, because these are not pure gauge, right. This is not QB on something, right. This is just moving the D-instanton along the time direction.
So these are the modules. You have
Exactly. So, you have to integrate over it, right.
Ah.
So, you have to separate them out in the perturbation theory and integrate over them at the end,
Yes.
right. So, that is what you are doing here, right. We have to remove them explicitly, okay, and then at the end you have to integrate over them.
Yes.
This is like how you take determinant prime for
Exactly.
exactly.
Yeah.
Rid of that
Yeah.
part of the determinant. Right?
Exactly.
And then you do
Yeah.
what you do with it.
So,
So this, with 2 D-instantons you could have relative this thing we haven't done.
no, that I think will be more complicated, right. You still have to separate it out, you have to do the integral, right, but that integral has to, I mean it will involve a non-trivial integral, right.
But in principle, there's no problem.
In principle there is no problem, yeah. You just have, you know what to do, you just have to separate it out and integrate over phi's, the 2 phi's at the end.
But there you will separate out the collective mode, the overall center.
No, both, because both are 0 modes there, right. Even the non-collective mode,
Because there is no interaction. between-
Quadratic order.
quadratic order, right. You have to separate those out.
And the effective action.
The 2 phi's, I mean instead of having 1 phi you will have 2 phi's, right. So, the center of mass phi, right, the dependence on that is trivial, right. You know what the dependence should be, so you produce a energy conserving delta function. The other one you have to work out what the action is, right, the cubic and higher order terms, and then you do the integral at the end.
Let me see if I understand it right, you correct me.
Yes.
From this formula
No, it doesn't say that. It doesn't enter here, yeah, in the action.
Therefore, this formula says that you replace this integral with 0.
No. No, because you still have to do path integral, right?
So now you have
Because
measure
see,
and
this
do
says
path.
only in the kinetic term it doesn't enter. In the interaction term it can enter,
In interaction terms it can enter, yes.
right?
So you have a path integral to do.
Yes. That's exactly the point, right? For the collective modes, you have to separate them out, you remove them from the propagator, and then you do the path integral.
But in this, I'm saying this again, because it does not enter the kinetic term, I don't even have to invert this mode.
Exactly, we are not doing it.
We don't even have to bother about it because I don't have to invert this.
No, but it's there in the path integral.
In the world sheet integral, it's there, right? See, in the world sheet path integral, in the world sheet description, you will see this time. If you,
This is like an infinitely strongly coupled mode.
It is infinitely strongly coupled mode, but in string field theoretic formalism, it does not enter the kinetic
True.
term. It enters other things.
I agree.
Therefore, for inverting the kinetic term,
You don't have to
worry
invert.
about
No,
No,
but you have to do the integral.
yeah, we have to worry about.
See, you have to do the path integral at the end, right?
it. Yeah.
Yeah. See, I mean, okay, if you do string field theory analysis, you will never include this, right? But what you do is you have the world sheet expression, right?
So from world sheet perspective, it is totally mysterious. This was
Exactly. So from the world sheet perspective, I am saying that whenever you see a 1 over q pole, you subtract it. That's exactly equivalent to this.
exactly equivalent to it because it does not enter
Exactly.
the kinetic term.
Yeah, it doesn't enter the kinetic term. Eventually, we have to do the integral.
Eventually, then you have to do the integral because you have a measure in this language.
Exactly. That's right.
You have a measure and other things.
Exactly.
It's sort of like a Wilsonian thing.
Hmm.
You've got
Exactly.
the lightest field, you find the effective action for that, and then integrate over the lightest.
Exactly. That's right. Okay, but now let me describe the really problematic ones. And that is the zero mode from the ghost sector. Okay, by ghost sector, I just mean that things which involve only ghost fields and not matter fields. Okay, so these satisfy Siegel gauge condition, right? Okay. These will have exactly the same problem. Okay. So if you look at the world sheet expression, right, the 1 over q poles will not only come from the good ones for which you know how to handle, right, but also for these. Okay. But these are not collective modes, right? So it's not clear a priori what to do with these, right? How to handle these modes.
You still know how to do path integral in this formalism.
Well, but the path integral you have to do with zero integrals, right? In fact, the path integral, as we will see, okay, is actually 0 formally. Okay, because we will see what the problem is and how to repair it. Okay, and we will see that the path integral is 0, right? But we know what the 0 means. In this formalism, it's hard to see what's happening.
Can you please repeat what the problem is?
Because these are L0 equal to 0 states, right? So they'll have exactly the same problem,
Yes, yes.
right? So in the world sheet integral, right? When you have the integral dy, for example, the analog of integral dy, we saw some poles, right? Now we'll get a y inverse pole, right? The ones which are associated with C del x, corrective modes, that we know we are supposed to remove it, and then the corrective coordinate integral will impose energy conservation, right? These zero modes are unphysical, right? They have no physical interpretation of what.
They do not appear as external states.
Oh, they don't. Not only they don't appear as external states, right? There is a physical reason for these zero modes to exist, right? From the point of view of D-instantons. Okay. So the fact that they have appeared, yes.
This is part of redundancy of the action.
We'll see how to deal with this, right? That
But
so.
don't you have some insertions? Let me ask this. In
Yes.
this formalism, not in world sheet formalism. In this formalism, these are zero modes.
Yes.
Now, at least in the kinetic term, they do not do anything, but they can do something. In other
Yes.
words, now I have to do path integrals over them, but there might be insertions. And with insertions, that
but what I am going to show is that actual path integral is 0. So, whatever you do, right, if you just try to do the path integral over these at the end, right, you should get 0, because actual result is 0.
Yes.
Okay, but you don't want 0, right, at the end. Okay, so that 0 has to be identified why it is 0, right. I'll show why it is 0, and then I'll say why, I mean, what is the what is happening, right, how to repair it.
That's the
Yes.
that's the identity operator, and this one is C del square C.
Exactly, this is C del square C. Okay.
The path integral is becoming 0 instead of infinity because
It is Grassmann, yeah.
Grassmann.
Grassmann, exactly. That's right. Okay. So let's first discuss the what we do, right, and then we will see that if you could do this, right, you will actually would have gotten 0 answer and you wouldn't know what to do with it. Okay. But we will see that there is a different way of looking at it, which will tell you exactly what the 0 means and what you should do with it. Okay. I think you are not looking happy, but let's go ahead and see what is happening. Okay. So to understand this, let's look at the full set of L0 equal to 0 states.
Including the matter sector.
No, in the host sector. Matter sector you already know what to do. Right? So matter sector is not a problem. Okay. So let me expand psi as psi 1 C0 on 0. Okay, so here the way I have chosen the size, these are the original size. Okay, you can see that these have ghost number less than or equal to 1, and these have ghost number larger than or equal to 2. Okay. So the Siegel gauge, well, it's not a gauge choice, but it's other slicing. Okay. This corresponds to setting psi 2 equal to 0 and psi 2, sorry, not psi 2 equal to 0, psi 1 equal to 0 and psi 2 equal to 0, right, because these are our psi lower tilde, because these are not unhidden by B0, right. So Siegel gauge sets all these 2 equal to 0. Okay. The original choice corresponds to setting psi 1 equal to 0, psi 2 equal to 0. All the host number larger than or equal to 2 states equal to set equal to 0, right. So let's see what happens if we use the original choice. Okay. So if you use the original choice, you can show the action, the kinetic term of the action just becomes psi 1 square and no dependence on psi 2. Okay. So still 1 0 mode remains. Psi 1 nothing depends on psi 1. Sorry, nothing depends on psi 2. Okay. But in fact, what one can show that after you have integrated out everything else, okay, which you can do, those you can do by Siegel gauge, right? L0 non-zero, right? L0 positive or negative you can do in the Siegel gauge. After you have integrated them out, okay, the psi 2 dependence completely drops out of the action. Okay. So now the path integral just has an overall integral d psi 2 factored out, okay, which doesn't do anything, and then the rest of the integral which depends on psi 1, integral d psi 1. Pardon?
Unless you have any insertion.
No, even the insertions, right, are with host number, the physical insertions are with host number 1 sector, right?
Yes, goes number 1 sector. Okay.
Okay. So psi 2 is host number 0.
Right.
So there is no psi 2 in the insertions also. Okay. So psi 2 just completely drops out. Okay. So this is like you are factoring out a overall gauge volume.
Overall gauge.
Okay. Except that this is not a gauge transformation because QB on 0 is 0. Okay. This is like some global symmetry. Okay, you are not, it does not give any 0 mode in the path integral. Is that point clear? See, anything above, anything which has L0 not equal to 0, you are using Siegel gauge, right. So, there of course the kinetic operator is invertible, right. So, the only issue is whether in this sector there is a non-invertible operator, right, non-invertible term. Okay. What I am saying, in this sector with psi upper 1 and psi upper 2, this is of course invertible because we explicitly have a quadratic term. Psi upper 2 does not have a kinetic term, but psi upper 2 never enters anywhere. Okay. In fact, its Gauss number less than or equal to 1, so it is not a physical field, right, and by the argument that I gave, it just decouples completely from the action. And from that there is no dependence on psi 2, right. So, you can do this integral at the end after you have integrated everything else.
There are extra gauge factors also from Gauss number 0, -1 and so on, which are overall factors we never cared about.
No, those factors are not there anymore because you have chosen Siegel gauge for those. So, we had to, the first choice that we made, right, had all those integrals, right.
Oh, now it's a different
Which, yeah, which could have been, which could, at that level, I mean, you could factor it out. The only problem was that the integral couldn't be done using perturbation theory, right, because of the 0 modes in the kinetic operator, right. Now, the point is whatever 0 modes we have, okay, are for those which completely decouple anyway, right, the psi upper 2. Okay, so they factor out.
So this is some kind of global symmetry.
This is some kind of global symmetry, exactly, generated by vacuum, right. It is global symmetry, but you are supposed to mod it out. That is why this integral over psi 1 is basically saying that, sorry, integral over psi 2 is basically saying that you are supposed to mod it out, but it does not give any shift in any of the fields, right, unlike gauge symmetries. The gauge symmetries are problematic because it shifts fields, right, like mu goes to del mu lambda, mu plus del mu lambda, right, and then del mu lambda is the 0 eigenvalue of the kinetic operator. It is not like this.
But for global symmetries, I never divide by the volume of it.
You could say that there is a rigid symmetry which is gauged. See, this is 0-dimensional theory, right. So, everything is, I mean, global in that sense. There is no space-time dependence anywhere. Right. It just so happens that this particular symmetry, right, does not generate a inhomogeneous term, right.
I mean, it seems to be even more stronger, like no field is transforming.
No, the nonlinear transformations are there. This particular if you take the gauge transformation generated by this, right, the nonlinear terms do transform, right, but there is no shift. But it in the action, it does not, the corresponding host does not appear in the action. Okay. So, then the prescription is that you remove all all integrals of this kind, okay, whether it is coming from C del x or from these. In perturbation theory, these are the ones which appear, right, because perturbation theory always, or the world sheet formalism always gives in the Siegel gauge. Okay. So, in the world sheet formulation, these things will also contribute, right, but we said that we will remove those, right, because that is not the basis you are using anymore. So, we will remove all Q inverse, dq Q inverse. Okay. What we had said in the first day, except that we did not, I mean, take into account these. Okay. But even after taking into account these, you just remove all the Q inverse poles. Okay. But what it is saying now is that you have to include the contribution of psi 1. Okay. This you have to do by hand explicitly in the calculation. Is that clear? Okay. So, let me give an example.
So this psi 1 square came only from the kinetic term.
Only from the kinetic term.
Psi 1 square coming from other interaction terms.
Not, yeah, psi 1 of course is interacting. So, psi 1 certainly interacts with the other fields.
So you had kinetic term and extra.
Exactly.
This psi 1 square came from the kinetic term.
Exactly.
And there could be additional factors of psi 1 coming from the interaction.
Exactly. Psi 1, psi 2, psi 3. Psi 1 phi square. Right.
But this is the factor which comes from kinetic term, which we have to put by hand. The parts that coming from interaction will automatically get generated when we consider them external?
Vortex, yes. Okay, we'll see. I mean, what it means, right? So what? Okay, in practical terms, what does it mean, right? Let's look at the calculation that we did last time. Okay, we are trying to calculate the 4-point function of phi, right? We use a Walsh-Lee expression for the 4-point function of phi, okay, and then try to repair it near y equal to 0 and y equal to 1. Okay. But what it misses is this diagram. Because in the Siegel gauge, we will not have this, right?
Do you need to make sense of this all in Siegel gauge?
No, you have to go out of Siegel gauge because Siegel gauge has that problem, right? I don't know how to make sense of this in Siegel gauge. See, the Siegel gauge, the problem, see, the problem doesn't show up at tree level, right? Because these have Gauss number not equal to 1, right? These are not classical fields. So the problem actually is in loop level, but to repair that problem, okay, we have to introduce this field psi 1, which actually is a physical field, right? Classical Gauss number 1 field. Okay. Once that is there, okay, and we are saying that we will not set psi 1 equal to 0, right? We will use that as path of the path integral. We will get integrals like terms like this.
This will never come in Siegel gauge.
This will never come in the Siegel gauge.
But you are making the point that in this other gauge you can see that this term is there from kinetic term.
Exactly. It's not other gauge, it's like other slicing, yes, whatever. So in this particular slicing,
It's a different canonical frame.
exactly,
In which you see that
this term should be there.
Of psi 1.
Exactly.
So, in some sense, I feel that one was lucky a bit because here the remaining things that appeared at L0 equals 0 were in pairs. Because you use Siegel gauge.
See, that will always happen.
That will always happen.
Yeah, because this pairing preserves L0. So if you look at all the L0 equal to 0 states, the full set of L0 equal to 0 states, they will always pair.
There will always be a pair subset.
Exactly, right? And the question is, from the L0 equal to 0 sector, you just choose a defined pair. Right?
So could I think of it this way? That I do the integral over all the non-zero modes in Siegel gauge.
Yes,
I get this effective action, and then for this effective action, I choose a new gauge.
exactly.
Exactly.
That's
Then
right.
you get right answer.
Yeah.
But it's also known that this Siegel gauge was slightly bad in the zero mode sector.
Yeah, certainly.
So therefore it's not very surprising.
Yeah.
Oh, I'm sorry.
No, it's true. It's that I mean, this tells us what to do in the zero mode sector.
Couldn't you have invented some hybrid thing in which you remain in single gauge for the matter sector and use this stuff that's
Not for the whole Gauss sector, right? Because there are pure gauge states purely in the Gauss sector, right? So even the Gauss sector is the kinetic term will not be invertible. Right? So it's best to do it in the zero mode sector, right? Because see, the advantage of using Siegel gauge is that then you can make direct contact to the Walsh-Lee expression, right? You don't want to use string field theory from the beginning, right? It's a very, I mean, you have to do infinite sum and so on. Walsh-Lee theory automatically has done that infinite sum, right? So it's only when you the Walsh-Lee theory seems to fail that you try to use string field theory.
So it's like what Sridhar was saying, that I think of the first doing the Wilsonian.
Wilsonian, for which you can just use a Walsh-Lee description,
Yeah, and now on this
and then you do this different gauge slicing here, different
L0
slicing.
equals 0 states I need to
Exactly, that's right. Only for L0 equal to 0 state, you be careful and do a different slicing.
Reduced to a very small problem.
Exactly,
So now somehow this diagram will give me minus gamma square.
exactly,
Cancel it.
exactly. So this diagram gives you the minus gamma square, which cancels that gamma square, right? So basically, this is so this propagator is minus half, right? The psi 1 propagator is minus half. You calculate the vortex from here, right? That's the 3-point function f1 dot c del x of 0, f2 dot c del x of 0, or maybe say f3, doesn't matter, it's cyclic anyway. Because it's this one, right? The vortex operator is del c. Okay. So you have to do a little work because this is not primary, right? But yesterday we already worked out what this is, right? So you basically use that. Okay. Calculate this 3-point function. Those are the ones which are going into the vortex. vertex, you multiply by the propagator, and at the end you get the minus gamma square. Okay, which
And if you keep the alphas, then the whole thing.
exactly, whole thing will be independent, right? But what this is saying now is that in any loop amplitude, tree amplitude, right, you have to do this, right? Whenever there is a degeneration, right, and there are plenty of degenerations in loop and tree, right, that besides what you get from the worldsheet after regulation and so on, right, after all this prescription, you also have to explicitly check the psi 1 propagation, right, because that is not included in the worldsheet description, right, that has to be explicitly put in the answer.
What guarantees that you are not missing anything? Because in the Siegel case, if I stick to the Siegel case, then I will definitely miss this side one. So
But the answer will be ill defined, right, as you can see, because you have the 0 modes, right.
But then that's why you go to the second choice and take the side one contribution and put it back by hand.
Not by hand, I am just saying that BV allows you to do a different slicing,
Yeah.
right. I just did a different slicing. See, BV allows you to do any slicing. The only problem is that if the answer is ill defined, right, then you don't know what to do, right. Just like in the original slicing that we do, just all the psi r's 0, right, psi lower r's, that is a perfectly good answer, except that you couldn't do perturbation theory with it, right. So it's not a BV. So according to BV, you can do any slicing that you like, right. It's just that some slicings are useful to do calculations, right. So here the slicing that is useful to do calculations, right, seem to be that you use the Siegel gauge like slicing for all L0 not equal to 0 fields, and for L0 equal to 0 sector you just use different slicing.
And again, you got rid of this integration d psi 2 by some principle. You said this is gauge or something. You don't
Yeah.
want to include it.
Because it's just overall factor, right, it doesn't depend on any field.
Doesn't depend on any.
It doesn't come in the amplitude.
Exactly, yeah, right. From the path integral perspective, it's just integral of d psi 2 and nothing else, right.
It is an overall factor.
It's just an overall factor. Right?
Like a decoupled free theory.
Exactly, it's like a decoupled free theory.
So Ashok, if the worldsheet theory is missing this entire mode, then should I not just go back and worry about all computations?
See, when you do the usual computations with finite momentum, right, this mode, the 0 momentum is a set of measure 0, right. So you don't really worry too much about this, right. Here the problem is severe because there is a momentum, right, and that's why the 0 momentum, everything is 0 momentum, right, and one mode can make a difference.
So never in closed strings I have to.
Yeah, I think for closed strings you don't have to worry about this, at least not in amplitude calculation, right. Sometimes when people calculate the effective potential by setting the momentum to 0 from the beginning, then you have to worry about this.
This gauge was bad for 0 mode, so use a different. Use a different.
Yeah,
slice.
except that you don't call it a gauge fixing, right. It's not a, it's a different slicing of the, yeah, exactly, different choice of polarization.
The fact that there was this decoupled free mode,
Yes.
is that something you knew beforehand or you knew?
Well, in a sense you knew beforehand because this is the gauge transformation is generated by ghost number 0 states, right, and in the ghost number 0 sector there is a vacuum, right, which is annihilated by QB, identity operator, right. So you knew that there is a mode that is basically pure gauge. It doesn't have to be gauge fixed. See, normally you gauge fix because when you make a gauge transformation, it shifts the field, a physical field, right. That's why you gauge fix. Here it's not shifting a physical field. That's in hindsight you certainly knew that there is a gauge transformation of this kind, right. Again, in normal string theory one doesn't worry about this because it's a set of measure 0, right. So you, it appears precisely in the 0 momentum sector. But for D-instantons, one has to worry about this. Yes.
If you don't mind clarify why again side upper 2 does not appear in the action.
Okay, because of the ghost number argument, right. Because after you have integrated out everything
With L0
with L0 not equal to 0 states, right? The only states that you have are psi 1 and psi upper 1 and psi upper 2, right? Psi upper 1 is ghost number 1, right? And we know that for an n point function, the total ghost number has to add up to n, right? So that's why the psi. So this is like you are doing the original slicing for this case, right? Except that now the original slicing is a good slicing, because the gauge that 0 of the kinetic operator is not there.
So even in single gauge, psi upper 2 would not have been really a problem.
Would not have been?
A problem because it has no. Their ghost numbers fixed.
Yeah, exactly.
Sorry, but what would the insertion of psi 2 even have meant? Because it's just an identity operator.
You have just put identity in the amplitude, right? But the point is, it's not, once you put an identity, right, even though it's identity, it's not nothing, because you have increased, it doesn't mean you have not inserted anything, because it increases the number of punctures, right? And once you increase the number of punctures, you also have to put a B, right? And that's what kills it.
Can you say, sorry, I don't get this clearly. Why, so this psi 2 generates some sort of a gauge transformation.
Yes.
And why was that totally trivial if you give some arguments, say why
That it doesn't, it generates gauge transformation, it generates a transformation, but it doesn't generate an inhomogeneous mode, right? See, the gauge transformations cause problem. See, normally the kinetic term in a gauge theory are not invertible because there is a inhomogeneous mode, right?
Yes.
There is a del mu lambda which you cannot invert, right?
Right.
But if there are no such modes, right, then the gauge transformation, it's like a global symmetry transformation, right? You are modding out by that. So then you don't worry about invertibility of the kinetic term, right?
Yes, if it does not generate.
Exactly, and that's what happens because QB on this is 0,
T when this is 0, yes.
right? So that's why there is no inhomogeneous term in the gauge transformation law, right?
Ashok, just to integrate all this with your earlier lectures, you also said that just when she and et al. Looked at the 2-point function, there was the issue of what would have been two disconnected diagrams and what is the relative weight.
Yes,
And
not relative weight. See, relative weight is fixed, is a relative cutoff. So there what happened was that you had this, this was one contribution to a 2-point function of closed strings, right? And the other one was this. These are of the same order, okay? Both are divergent. Okay? This is divergent when the annulus, the handle becomes long. This is divergent when one puncture comes close to the boundary, okay? But that's equivalent to something like this. Okay? So this diagram is divergent, this diagram is divergent, right? Both are logarithmically divergent. There is a dq by q kind of divergence. Okay? So the idea is you cut it off. Okay? But if you don't do string field theory, right, then you can cut it off. It's logarithmic divergence. You cut it off. You cut it off. Right? They have opposite sign, so apparently they cancel. But where you cut off is up to you, right? So that becomes, yeah, it's finite but ambiguous. Right? So that was the ambiguity. But if you do everything consistently from string field theory perspective, then there is no ambiguity in where you cut it off. Like yesterday when you did the calculation, right? I mean this y integral, we knew precisely which part of the y integral corresponds to q running between 0 and 1. Right? Once you have chosen the f's, right, you fix the range, I mean where you should cut it off, right? And the point is that once you have fixed the f's, right, you have to use the same f's in all the diagrams. Okay, that's how you relate the cutoff that you have to use here to the cutoff that you have to use here. Right? If you just think it from the world sheet perspective, right, there is no reason why there is any relation between that cutoff and this cutoff. Right? Both are divergent and you are just regulating it.
But is it a theory should come with this single cutoff? I mean, in quantum field theory, for example.
But the world sheet, this is, yeah.
we always
Yeah, but the point is there you work on a fixed surface, right? See here the cutoff is coming because of the modulus integral, right? Not the UV cutoff of the worldsheet theory.
So string field theory is automatically giving you the relative cutoffs.
Exactly, that's right. Right? I mean, individually the cutoffs are arbitrary because that will depend on the choice of the f's, right? It's like if you change the alpha in yesterday's example, right? The range of y that it covers is different, right? But it's just that once you have chosen one alpha for one diagram, right? It's the same vertex you have to use everywhere, right? And that's what relates these two cutoffs.
We discussed the propagator of string field theory in detail, but about the vertices, I mean about the interacting terms, is it that one just computes this 3-point function with some choice of f's?
Well, and 4-point function and 5-point function exactly.
So how is the choices of f related across the 3-point choice?
Yeah. So the okay, it's the choice of f and also the range of integration. So for example, take you suppose it starts with a 3-point function, the f's are arbitrary. Okay, but after you got the 3-point function, suppose you look at the 4-point function, okay, you got this is a 4-point amplitude, right? This gave some range of y, right? Say y less than or equal to 1 and then greater than 1 minus something. Okay. So, and similarly y equal to 0 some other diagram. Okay. Rest of the y region has to be covered by the 4-point function. Okay. But there is also something more that you have to do because which I didn't need yesterday, but given a gluing like this, right, it automatically also specifies what the local coordinates are at these 4 punctures now, right? Because here there is W1, W2, here W1, W3 and W1, W3, right? Those are all given in terms of Z now, right?
Yeah.
So local coordinates are known. So as you glue here, so at this point you you glue a 4-point function, right? I mean the 4-point function covers the rest of the range. You have to make sure that the f's that you choose for the 4-point function matches the f's that are induced from this at the boundary, right, at this value of y. Right. In the interior again you can choose them any way you like. Okay. So the constants are mild, that you have to make sure that the vertices match, right? And this translates, if you don't, from this perspective it's like you want to reproduce the string amplitudes and that's why you are doing this. But instead of this, if you try to solve BB master equation, you get exactly the same constraints, right? The way you have to build the 4-point function is precisely this way, right?
Roughly the ambiguities keep on increasing?
Yeah, it keep on increasing. So that's there's a lot of ambiguity, okay? But what one can show is that all of these ambiguities are just field redefinition, right? And the way you show it is that you assume that you make a small deformation of all the FIs, right, subject to the constraints, right? And then you can show that induces a symplectic transformation on the fields, right, which you know is doesn't do anything, right? If you make a symplectic transformation on the fields, right, it's a symmetry, right? So it will give exactly the same amplitudes. So that's why we had known from the beginning that if you do things correctly, the results would be independent of alpha and gamma, right? It was not obvious because in the intermediate stage it depends highly non-trivially on alpha and gamma, right? Okay, so the point is if you do BV correctly, if you do the BV formalism correctly, it should automatically come out to be independent of alpha and gamma, right? But it's not obvious in the intermediate stage.
So if I can ask a slightly more general question, but we can come to it later, which is Euclidean D-branes give important contributions in all kinds of situations other than the case she et al. Looked at. For example, Euclidean D3 branes
Exactly,
give rise
yeah.
to important contributions and superpotentials. Now, in some of them, probably the answers people are using, which were just through holomorphy, etc., are correct. But do you feel that there are other contributions that have been considered which might be similarly missing? Something?
Yeah, I think people haven't really considered very much the systematic corrections. The leading part, right, doesn't suffer from these.
The leading also involves one Euclidean instanton and so on.
Yes, so one Euclidean instanton, but suppose you are only interested in disk amplitudes, right. So, one point function of closed strings on the disk, right. That will not suffer from this problem, right. It is only when you try to go to say 2-point function of closed strings on the disk. This is one higher order compared, say leading order here, right, will be just this, which has no degeneration, right. If I try to calculate 2-point function of closed strings due to instanton, this is the leading term, right, because it is 1 over Gs times 1 over Gs, right. So, these kind of problems come from the first subleading order. Okay. But for example, this Mike Greer and Gutperl, they wrote this modular in type 2B D-instantons, right? They wrote a modular form. Okay. That has a structure, it will be 2 minus 1 over Gs, and then the whole series expansion in Gs. Okay.
They were computing some R square F2.
Exactly, the coefficient, right. So, they guessed what this is just by using S duality, right. But those coefficients in principle can be calculated in string theory, right, and those calculations will have to deal with these, right, because this feature that we saw, right, that there is this there you have to switch in the 0 mode sector, right. They also they are in superstring theory, right. It is not specific to bosonic strings, right. Even for superstrings you see that in the ghost sector, if you insist on being Siegel gauge, there are these spurious 0 modes, right, but precisely in the 0 mode sector you can go back to the original slicing, right, and you have exactly the same structure, right. There is an additional field that propagates. So, I think those will have to be taken into account if you try to reproduce these higher order terms in the expansion.
Is it the time to ask slightly vague questions, or do you have to?
No, no, it's fine. Yeah.
Okay.
Maybe we should first.
Yeah.
Thank you.
Okay, I have a very vague question that probably means nothing, but let me ask it. There's this huge gauge symmetry in your string field theory. But to see it implemented, you needed this vast number of auxiliary fields. Now, if I try to write down some sort of field theory with only the physical fields, or maybe you can't get away with only, but integrating out as many auxiliary fields as I can.
Yeah.
Some of these gauge invariances, of course, let's say the Yang-Mills gauge invariance is very familiar, right? In that field theory with the, it gives you a familiar gauge transformation. So the question has two parts. A, is this gauge invariance somehow special? Is there something different about this one because it comes at massless level than the other ones? And B, can we get some rough sense of how it acts on the physical field? How the higher guys act on the physical fields.
Sorry, which gauge transformation special? The gauge?
The Yang-Mills gauge.
The Yang-Mills gauge.
Yeah. See, the point is that the gauge transformations, the action of the gauge transformation on the fields is not a gauge invariant, or no, it's not a field redefinition independent question, right? So, if you want to know, see Yang-Mills gauge transformation, right? There is a way to integrate out everything else, right, and get down to just the massless sector, right? You still have the full BB structure in that sector, okay, and there will be gauge invariance, but it will not look like Yang-Mills gauge invariance except at the lowest order, right? But it has exactly the same content as Yang-Mills gauge invariance, right? Because the fields of string field theory are related to the Yang-Mills fields in a non-trivial way, right? And it had to be that way because the string field theory is finite, right? Yang-Mills theory is not finite, right? And so the actual vortices that you will see have these exponentials in momentum, okay, which make the loop integrals converge.
That's a bit sorry to interrupt, but so you can nevertheless, despite these differences in the vertices and so on, integrate out all the heavy modes and just create a.
But still, the Yang-Mills field will have a momentum dependence. See, the point is there is a way to do this in string field theory. You integrate all the heavy modes, right? You just write down a BB master action just for the Yang-Mills fields. Right? That action satisfies the full BB equation and it's manifestly finite.
And it's arbitrarily non-local. I mean,
Arbitrary non-local, exactly, because you have integrated all the heavy fields, right? But So, the point it will not be Young-Mills, right, but then you have to take the low energy limit, okay, in which case it will become Young-Mills, right, because the exponents they suppress the corrections are like e to exponential minus alpha prime p square, right. So, if you expand in p, right, then you will start seeing more the structure of Young-Mills theory.
But perhaps I can reword. In S matrices, when you compute S matrices with Young-Mills, at least in a particular choice of gauge, you know that the gauge invariance tells you that shifts of epsilon proportional to k give you the same S matrix.
Yes.
Is there an analogous statement for the higher spin field, the higher spin massive fields, coming from higher gauge invariances?
I think they are probably not, because this, I mean those are like I mean already I mean there are Stuckelberg kind of fields, right, but you don't see them explicitly for higher spin fields, right. You will not say gauge invariance in that way,
Exactly.
because it's spontaneously broken.
Because it's spontaneously broken.
Exactly.
Right. Can that statement be made a little more precise?
In the spontaneously broken phase also you might have word identities.
So you have order identities, but not
No.
simple order identities like the one, what Siraj was asking, right? Yeah, you certainly have order identities, because for string field theory has infinite number of gauge symmetries, right? So for all of them you have order identities of the S matrix.
And how do we see that these gauge invariances are spontaneously broken? What is
Only one way to see this is that they are massive fields, right?
And just
And-
when I look at the action of the gauge transformation itself.
Yeah, maybe one can say that even in the zero momentum sector,
Ah,
there is a non-zero shift.
I see.
Exactly. Yeah.
Even in the zero moment of the same.
Even in the zero momentum sector, right?
Yeah. Okay.
There is a non-zero shift. See, normally for gauge transformation, right? If you take the constant gauge transformation, then the fields the gauge field doesn't transform, right?
Yes.
I mean, at least at the leading order.
If it is broken or not.
Exactly.
Okay,
That's
that
right.
you can yes.
Yeah. Right. So what will happen if in the other case, in string field theory, is that even if you take zero momentum sector, right, space-time independent, yeah, then you'll get a non-zero answer acting on the
Just
QB.
following up on that, if you have a normal gauge symmetry, that's a Young-Mills gauge symmetry, and it's spontaneously broken, you get these W bosons,
Yes.
which are sort of like your higher spin fields. But the scattering of W bosons with the basic interaction terms are constrained by the original gauge invariance.
That's true.
And so, can one derive general properties of string amplitudes?
The
from
word
this
identities.
statement? Yeah, the word identities.
Yeah, I think that one can. I mean,
And it's these are familiar properties?
yeah, I would say think so. That I mean, for example, massive vector boson, right? Whatever word identity one has there,
Right,
I think will come out from string field theory,
right,
right? Because there is a underlying gauge invariance,
right,
right? It's just spontaneously broken.
right. So what I was wondering was this. So suppose one could just list all these word identities. And then these in principle should constrain all string scattering amplitudes, right?
Yes.
One is completely determined.
That's right. Yeah.
So maybe that's a way of thinking of, could that be an efficient way of actually calculating string amplitudes? By listing the word identities and then finding solutions. It's completely
Yeah.
I'm
Yeah.
sorry.
I don't know. Meaning,
Yeah.
yeah.
Any computation, maybe not all, maybe.
Yeah.
Even checking that explicit solutions agree.
No, that you can check certainly. I mean, if you once you write the word identities, right? I mean, starting from string field theory, one can certainly write word identities, right? And you can go on shell.
Yeah.
I mean, you have properties of off shell amplitudes, and then you can go from on shell, right? And
And then the hope might be that once you do that, you go on shell and you get relatively simple equations you can write down and try to make sense of. Or maybe it's just be very complicated.
yeah, maybe what one can do is to look at W boson word identities,
Right,
right? And then just look at open string field theory at one higher level.
right,
There are massive vector fields, right?
right. And look at it.
And then compare the word identities that one gets there with the W boson word identities,
Right,
right? Just maybe just for the 4-point function.
right, 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 right.
Yeah, but even for W boson, I think word identities are complicated, right? It's not easy to. Meaning is what kind of simple word identity will you get for the W bosons?
Right. So let's say you would be able to just in terms of the action that it has a particular, I mean, it relates the coupling between Higgs. It would relate the coupling between Higgs and Higgs Higgs WW and the gauge boson couplings. Right? I'm saying just from the Lagrangian. There was some
The number of parameters.
number of parameters is smaller. It's smaller than you could just completely write down.
The same thing.
Exactly. So the
Let's see. If you think of Higgs as a single scalar,
good single complex scalar, yeah.
complex. No, I mean really. I mean think of really real Higgs. SU2.
Okay, fine. I see.
Okay, standard model I was thinking, but okay.
Fine.
Anyway.
I was thinking of U1. But
Okay,
yeah,
so U1 with Higgs. Yeah, so I'll think then for U1 with a Higgs, then it's a real scalar, right?
Yeah.
Ultimately, you will get a
I mean, he's saying after unitary.
yeah.
after you, yeah.
When after you, I mean, you look
Yes.
at the physical content,
Yes,
right?
yes, yes.
It's the theory of a single scalar interacting with a massive
Massive vector field.
vector field.
Exactly.
So what constraints will you have?
Right. So the original theory had a 5 to the 4 coupling, let's say for the Higgs, a 5 squared, 5 to the 4 coupling, and gauge coupling for the gauge boson.
Yes. So 3 coupling constants.
3 coupling.
Okay, meaning phi square is a mass term, yeah. And
Right.
now you have a mass of the W boson.
Now we have the mass of the W boson, we have the mass of the Higgs
Higgs,
field,
yeah.
and we have the coupling between the Higgs and the W boson.
Yes.
Normally you relate the longitudinal photons behavior
To the Higgs.
right?
Yeah, but
But just in parameters,
yeah, in terms of parameters, I'm just trying to see. Yeah, I mean, certainly you shouldn't be able to write down an arbitrary theory, but on the other hand,
what else could you?
yeah, this Tuchelberg allows you to write a theory only of the W bosons, right? Massive
Yeah.
W bosons.
Right.
And then you can just add a massive Higgs field.
Right. Right.
The question is the fact that this Higgs is the one which is responsible for symmetry breaking. What is the signature that it will have?
Right. Good.
I have to think, but I suspect it should because
Even I feel
the,
that.
the longitudinal
Yeah.
mode of the photon should be coupled, right, to some property of the Higgs.
Yeah, maybe phi square W square coupling will be
Yeah.
controlled. You cannot just add arbitrary phi square W square kind of coupling.
Yeah.
Yeah.
But
Hmm.
there is some interaction terms.
Hmm. Yeah. Hmm.
It should be there.
Yeah.
Then
Yeah.
you will see
Hmm.
some.
See, my feeling is that okay, that I think whatever identity you will get, right, is just an identity based on the fact that the massive fields cannot be coupled arbitrarily, right? The W boson, we can imagine that the W boson has become massive by some Stugelberg mechanism, right?
Yes.
Something which has become infinitely heavy, and then there is a separate scalar field that you add, right?
Yes. Yeah.
Then whatever constant you have on that theory
Exactly.
is what you can get.
Exactly. But this should now relate all the massive fields to each other, right? Because your gauge invariance completely fixed the string field theory action.
Yes.
So it should be extremely powerful in string theory. It should somehow be completely telling you the answers, right?
Yeah, maybe. Yeah, I agree. I mean, of course, yeah, in string theory, yeah. I mean, in essence, you can say theory is unique, but the question is how to get.
And you
Yeah.
also said algebraically you showed that the theory was unique using gauge symmetry.
That's true.
So it's
And the way
all
you,
the coupling
okay,
constants have been determined.
assuming that the BV formalism is the right one to use, right? You are saying that yeah, if you want to demand that solves BV master equation, then you can build the whole structure starting from the 3-point vortex.
So that sounds like there's some set of constraints you can write down that
Yeah.
effectively determine all things.
That's
Of course, it may be so complicated that it's useless. It may be the equivalent to saying construct string field theory.
Yeah.
But the thing you might get out of this is that it might be simpler when you go on chain.
Yeah.
because you're constructing string field theory option.
Yeah. See, BV has a formalism called minimal model, which I don't understand very well, but apparently that directly gives the S matrix. You remove all the unnecessary things, right, which maybe one has to try to understand a little better. Minimal model, it's called minimal model inside the in the BV formalism.
This 2D rational CFT.
No, no, no.
This is some
No, no, not BV. In the BV literature, there is some something called a minimal model, right? And what the minimal model is supposed to do, it basically instead of giving the string field theory action, it gives the S matrix.
So you don't have anything directly on cell.
Yeah, it somehow gives the directly on cell amplitude, but it has a BV structure.
So this
So-
is very, very interesting, but just to go back to the earlier comments, just so I understand it, you're saying, look, if we assume there is a BV formulation, then since the BV formulation is unique up to field redefinitions, since the S matrix is independent of field redefinitions, it proves there's only one S matrix. And okay, and now, okay, maybe
Yeah,
one can
of course you have to
prove it
start
in
from some data, right? I mean, some minimal data you have to maybe you have to put the torus, yeah, maybe 1-point function on the torus and 3-point function, right? Which are the starting
start
points,
the-
yeah, to start the iterative
Yeah.
process, yeah.
Okay. Just about the counting we were doing, I think it's 3 goes to 4 for the couplings for this U1 thing. The 3 being the gauge coupling, the term behind F squared, 5 to the 5 squared and 5 to the 4. And on the right hand side, once we take the massive vector field, there's the gauge coupling, namely the coefficient of F squared again, M squared for the gauge field, then the mass of the Higgs field, and the Higgs.
But that gauge coupling now can be absorbed into the W.
Well, then you could have
Scaling.
observed it in the earlier counting as well.
No, then the Higgs, there the field was charged. See, now the field is neutral.
Well, but there's also a phi square A square coupling.
5 square W, yeah, 5 square A square. That's probably what is called what will get
So if
controlled.
you try to do a rescaling, that term will change.
Yeah, I think that 5 square A square term probably will somehow get fixed.
Yeah.
You cannot add.
But in a sense, you have to add that coupling in the Stuckelberg with neutral scalar, and then its coupling should.
Yeah, I think the main point is that if you have a Stuckelberg field W, right, you cannot add arbitrary coupling to W, right?
And the scalar.
Yeah, I mean you break gauge invariance. I think the original Stuckelberg gauge, original Stuckelberg field, if you probably can think of this as a Higgs mechanism, where the actual physical Higgs goes to infinite mass, right? But it started with a gauge invariant action, right? And just like in the gauge invariant action, you cannot add arbitrary coupling to mu. Right? So after you have done the gauge fixing and make the W heavy, right? I think you are not allowed to add arbitrary A square phi square coupling anymore, or any arbitrary coupling of A.
Yeah, clearly it's fixed. If you do
It has to come through F mu.
Yeah.
Any additional coupling has to come through F mu, right? Besides the mass term.
Right.
But if you did do it, then you would get a different S matrix.
Yeah, and I think that will not be consistent. Internal that somehow will fail some internal consistency
That's the
of the
part
theory.
I'm not sure, but probably.
I mean, if you just have a massive W field, see, I think the
High energy. So this is
High enough scale, there will be some lack of unitarity or something.
maybe, yeah.
I think so. Because then it's like adding a separate massive vector goes on something coupling. which is
Yeah.
not right.
So it's not just gauge invariance; it's somehow high energy behavior,
Right.
right?
Right.
So just from word identity, I don't know whether we can. Oh, maybe the string theory word identity already know about high energy behavior. That's what you are saying.
In fact, if you go to sufficiently high energies, it is not spontaneously broken anymore. Effectively, the entire thing is coming back.
Yeah.
So therefore, the very high energy behavior of scattering amplitudes must be very constrained by this humongous
That's true.
gauge symmetry.
Yeah, yeah.
So is there some evidence of that, like the very high energy
Yeah, I don't know.
amplitudes?
Meaning this Gross-Mende calculation is there, but it's not directly related to the gauge invariance, right? It's not directly related to gauge
Yeah,
invariance.
it's not.
Hmm.
No, yeah, that's true. But it has an amazingly simple form.
To ask something vague, but say along those etc. lines, given the unique formulation, but the fact that you needed some input to start that, like the 3-point function and so on. What can we say about string amplitudes, scattering amplitudes, which is independent of the compactification? This is something that we discussed here also a little bit. Namely, take a compactification which has all kinds of, modes excited, RR fluxes, whatever, in some number of compact directions, some number of non-compact, say 3+1. And now, after specifying how much zeta does the S matrix for the massless fields, gravitons and so on in the 3+1 dimensions become unique, or is it totally unique to begin with?
At tree level.
No, but
Yeah, you are doing more generally.
yeah, now you have a formulation.
But then every compactification will give you a nuance.
Give a nuance,
Yeah.
but is there something?
But
which is-
that information will probably go in the spectrum already. Yeah, just massless one will not probably do.
Oh, you need the entire tree.
I
You
think,
need
yeah.
the entire tree level, the
Yeah.
leading spectrum,
Yeah.
and some more
Interactions,
data
yeah.
to start this.
Hmm.
Okay, yeah, you need all that.
Yeah.
But is there a universality at high energies for this scattering?
See, in some sense you will say yes, because
Then the details will not.
yeah, at high energy the details of compactification, no, that's why. That I think I can take this off. No, nobody is there. Yeah.
We can clap once more.
That's fine.
Let him
No, that's fine.
I know, so
No problem.